Hey there, dreamers. Welcome to Happy Sleep. Whether you're tuning in from a bustling city where the lights never quite dim, or a quiet town where the stars are still visible, whether you're winding down for the night or it's the middle of the day and you just need a moment of cosmic calm, I'm so glad you're here. Tonight, we're going on a journey unlike any other. We're going to ask a question that has haunted poets, scientists, and stargazers for millennia. Could we ever truly leave our galactic home? Could we venture beyond the Milky Way? It's a story of impossible distances, incredible technology, and the boundless human spirit. So, get comfortable, let your mind drift, and together, let's wander the cosmos. If this journey captures your imagination, if it helps you relax and drift into a deeper wonder, then please do consider subscribing to Happy Sleep. It's the easiest way to make sure you never miss our next adventure into the unknown. And I'd love to hear from you in the comments below. Tell me where in the world you're listening from and what time it is for you. It's always amazing to see our community of cosmic dreamers spanning the globe. Now, let's begin. Have you ever, on a perfectly clear, moonless night, far from the glow of city lights, looked up? I mean, really looked up. Not just a glance, but a long, deep, soul-searching gaze into that vast, star-strewn blackness. If you have, you've seen it. A faint, milky, ethereal river of light arching across the heavens. The ancient Greeks saw it and told a story of spilled milk from the goddess Hera. We know it as something far grander, our home, the Milky Way Galaxy. It's not just a smear of light. It's a colossal pinwheel of gas, dust, and over 100 billion stars, one of which is our sun, a rather average star on a quiet suburban street called the Orion Spur. We are, all of us, every person you've ever known, every mountain, every ocean, every whispered secret and roaring triumph aboard a spaceship called Earth, orbiting that sun, which is itself hurtling around the galactic center at hundreds of thousands of kilometers per hour. We are already cosmic travelers, but it begs a question, a thrilling, terrifying, profoundly human question. Can we, the inhabitants of this tiny pale blue dot, ever leave our galactic home? Can we step out from the Milky Way and into the intergalactic void? The short, honest answer, with our current understanding of physics and technology, is a resounding, overwhelming, almost laughable no. It is the most formidable challenge imaginable, a leap that makes climbing Mount Everest look like stepping over a crack in the pavement. But, and this is a very important but, the human spirit is not fed by short answers. It is fueled by the what if, the how could we, the audacious act of staring into the face of impossibility and asking, well, why not? So let's embark on a journey of our own, a thought experiment of epic proportions. Let's pack our imaginary bags with curiosity, leave our doubts on the launch pad, and explore the mind-bending possibilities, the terrifying obstacles, and the far future dreams of what it might take to truly leave the galaxy. First, we need to understand what we're up against. We need to grasp the sheer, staggering scale of our home. We often hear the numbers, but they wash over us. They are too big to feel. Let's try to make them feel real. Imagine our entire planet, Earth, is shrunk down to the size of a single grain of sand, a tiny, almost invisible speck. On this scale, how big is the moon? It's another, slightly smaller grain of sand about 3 centimeters away. Not too bad. And the sun? On our grain of sand Earth, the sun would be a large beach ball, about the size of a big exercise ball, located. Are you ready for this? over 100 meters away. That's the length of a soccer field. Our entire solar system, out to the orbit of Neptune, would span about 6 kilometers. You'd need to drive to really see its full extent. Now, hold on to your hat. On this same scale, where Earth is a grain of sand and the solar system is 6 kilometers across, the next nearest star system, Alpha Centauri, would be over 16,000 kilometers away. That's roughly the distance from New York to Sydney, Australia. All that emptiness, just to get to the next few grains of sand. And the Milky Way? This entire galaxy, containing over 100 billion of those star suns, would be, are you sitting down? About 100 million kilometers across. That's more than the actual distance from the real Earth to the real Sun. Our entire grain of sand solar system is lost, utterly and completely lost, in a volume of space so immense it defies all human intuition. So, we've established that the first and greatest wall we hit is distance. It's a word we use every day without really feeling its weight. We talk about the distance to the grocery store, the distance to the office, the distance across the country. These are distances we can comprehend. We've driven them, flown them. We have a physical gut-level understanding of what it means to traverse them. But the distances we're talking about now, the cosmic distances between stars and across galaxies, are of an entirely different breed. They belong to a category of scale that the human brain did not evolve to understand. Our instincts, our intuition, are completely useless here. They break down. They short-circuit. To truly grasp it, we have to perform a kind of mental judo, using metaphors and comparisons to force our earthbound minds to comprehend the heavens. Think of it like this. Imagine you're standing on a vast, perfectly flat desert that stretches out to the horizon in every direction. This desert is the emptiness of space. Now, in this entire desert, there are only a few dozen grains of sand. That's it. Just a few dozen. Each one of those grains of sand is a star. Our sun is one of them. The nearest grain of sand, our nearest stellar neighbor, Proxima Centauri, isn't a few feet away. It isn't a few yards away. On the scale of this imaginary desert, the very next grain of sand is over 40 miles away. 40 miles of absolutely nothing but flat, empty desert to get to the next tiny speck. That's the local density of our stellar neighborhood. That is the emptiness we have to cross. And how are we planning to cross it? With our current technology, it's as if we've built a little toy car, wound it up, and pointed it in the direction of that grain of sand 40 miles away. That toy car is our Voyager 1 probe. It is, without a doubt, a masterpiece of human engineering. It carries a golden record with greetings from Earth, sounds of our planet, music from our cultures, a message in a bottle hurled into the cosmic ocean. And it is moving. It's zipping along at a truly impressive 38,000 miles per hour relative to the sun. To us, that speed is phenomenal. It's over 10 times faster than a speeding bullet. If it could fly at that speed in our atmosphere, it could go from New York to Los Angeles in about 4 minutes. But out here, in our desert analogy, that blistering, unbelievable speed translates to something pathetic. Something laughably slow. If our toy car is moving at Voyager's speed on this scale, it would be inching forward at a pace so slow you couldn't even see it move with your naked eye. You'd have to stare at it for hours to notice it had budged a millimeter. At this pace, the journey to that next grain of sand 40 miles away would take not years, not decades, but tens of thousands of years. This isn't a journey. It's a geological process. It's like planting a sequoia tree whose seedlings your species' distant, evolved descendants might one day sit under. It's a time scale that dwarfs human history. Let's put a finer point on that 70,000-year figure for Voyager to reach Alpha Centauri. 70,000 years ago, what was happening on Earth? The world was a very different place. It was the peak of the last ice age. Vast sheets of ice, thousands of feet thick, covered much of North America and Europe. Neanderthals still walked the Earth, sharing the landscape with early Homo sapiens. The first cave paintings were perhaps just being conceived in the minds of our ancestors. If someone had launched Voyager back then, as the glaciers were at their maximum extent, it would only just now, in our lifetime, be arriving at its destination. All of recorded human history, the rise and fall of empires, the invention of writing, the agricultural and industrial revolutions, the digital age, all of it would have fit comfortably into the travel time of this, our fastest object. This is what we're up against. This is the reality of the cosmic distance scale. It's a reality that doesn't just laugh at our ambitions. It doesn't even notice them. It's completely indifferent. The universe is not designed for convenience. It wasn't laid out with our travel plans in mind. The sheer yawning emptiness is the default setting of the cosmos. Matter, the stuff that makes up stars, planets, and us, is the rare exception. The void is the rule. This emptiness, this incredible nothingness between stars, is called the interstellar medium. But it's a bit of a misnomer because it makes it sound like there's something there, like a medium. It's not a true vacuum, but it's so close that it might as well be. In the space between stars, there are, on average, a few atoms in every cubic centimeter. To put that in perspective, the air we're breathing right now has something like 30 quintillion molecules in that same cubic centimeter. A quintillion is a 1 with 18 zeros after it. So space isn't just empty. It's emptier than any vacuum we can create in our most advanced laboratories on Earth. It is the deepest, most profound silence imaginable. Now, imagine our little Voyager probe, this tiny, intricate machine, sailing through this incredible void. It's utterly alone. The light from the sun, from where it is just another bright star in the sky, not the blazing orb we know. It's been traveling for over 40 years, and in all that time, across billions of miles, it has not come close to anything. Not a single atom of its structure has collided with anything substantial from the outside. It's on the most solitary journey any human-made object has ever undertaken. It's a testament to our desire to reach out, to explore, but it also highlights our profound isolation. We are, for all intents and purposes, marooned on an island in a vast and empty sea. This is why the idea of leaving the galaxy is so monumental. It's not like packing up the car and moving to the next state. It's not even like the ancient Polynesians navigating vast stretches of the Pacific Ocean. In those ocean voyages, there was always something. The water, the wind, the currents, the fish, the birds. There was a medium to travel through and signs of life. Interstellar space, and especially intergalactic space, offers none of that. It is the ultimate desert. A voyage to another star is like trying to cross the Pacific Ocean on a raft. But if the Pacific Ocean were drained of all water, all air, and stretched out to be 1,000 times wider, the scale is simply not of this world. This is the fundamental problem that any future starfarer must solve. It's not just about going fast. It's about going fast for a very, very, very long time. It's about building a ship that can not only accelerate to a decent fraction of light speed, but also sustain itself, protect its occupants, and navigate the void for centuries or millennia. The distance is the immutable factor. It is the boss we have to work for. All of our technology, all of our cleverness must be bent to the singular purpose of overcoming this one simple, brutal fact. Space is big, and everything else is very, very far away. So when we talk about building fusion rockets or antimatter drives or light sails, we're not just talking about making a faster engine. We're talking about building a bridge across those 40 miles of empty desert. We're talking about creating a technology that can compress the incomprehensible vastness of time and space into something manageable, into something that fits within the lifespan of a hopeful species. The distance is the wall. Our imagination and our ingenuity are the tools we have to try and climb it. And as we'll see, that climb will require us to rethink not just physics, but the very nature of time itself. So we've established that our current speed is, well, let's be kind and call it leisurely for interstellar travel. It's the pace of a garden snail setting out to cross a continent. If we're ever going to get anywhere interesting before our species evolves into something else entirely, we need to pick up the pace. We need to stop thinking like pedestrians and start thinking like beings who understand the universe's rules. And the universe has a very strict speed limit. It's not posted on any cosmic signpost, but it's woven into the very fabric of reality itself. It's the speed of light, 300,000 kilometers per second. That's so fast that it circles the entire Earth about 7.5 times in a single second. Whoosh, you're around the world. Whoosh, you're around again. It's a speed so profound that it's less a velocity and more a fundamental constant of nature, like the gravitational constant or the charge of an electron. It's the universe's ultimate traffic law, and nothing with mass can ever quite reach it. You can get infinitely close, but you can never hit it. It's the final barrier. Now, let's put our Voyager probe's speed into this new, more realistic perspective. We said it was going 17 kilometers per second, which sounds fast. But compared to light speed, it's moving at a paltry 0.0056% of the cosmic speed limit. If the speed limit is 100, Voyager is doing 0.0056. It's not even crawling. It's essentially motionless on this new scale. It's like a single-celled amoeba trying to cross the Atlantic Ocean by doing the breaststroke. The commitment is admirable, but the timeline is absurd. So, what's a reasonable goal? What's a speed that's still fantastically, mind-bogglingly fast, but doesn't require us to break physics as we know it? Let's dream big, but practically. Let's aim for 10% of light speed. 10%? That's 30,000 kilometers per second. Let's try to make that number feel real. Imagine you're standing on the surface of the Earth, and you have a spacecraft that can instantly accelerate to this speed. You fire the engines. In the first second, you're already 30,000 kilometers away. You've instantly left the Earth's atmosphere far behind. In just over a second, you've passed the moon. Think about that for a moment. The Apollo astronauts took 3 days to get to the moon. You'd get there in less time than it takes to sneeze. The moon would be a momentary blur outside your window. Mars? At its closest approach to Earth, it would be a 2-day trip. Not bad. You could pop over to the red planet for a weekend excursion. The outer planets? Jupiter, which is over 600 million kilometers away, would be reachable in about 3.5 hours. Saturn in 7. The entire solar system, our entire cosmic backyard, suddenly becomes a local neighborhood. It shrinks. The distances that felt immense with chemical rockets become trivial. You could have a meeting around Saturn's rings and be home for dinner. This is the transformative power of speed. It literally changes your perception of the universe. It makes the vast seem intimate. But we're not just talking about touring the solar system. We're talking about leaving it. Our real goal is Alpha Centauri, that next grain of sand in our cosmic desert, 437 light-years away. At 10% of light speed, the math suddenly starts to become almost human. A light-year is the distance light travels in 1 year. So, if you're going 1/10 that speed, it will take you 10 years to travel 1 light-year. For a 4.37 light-year journey, you're looking at a travel time of about 44 years. 44 years. Now that is a number we can wrap our heads around. It's a long time, certainly. It's most of a working career. It's more than half an average human lifespan. But it's not 70,000 years. It's not a geological epoch. It's a time frame that fits within the scope of a single human life. This changes everything. It moves the mission from the realm of pure fantasy into the realm of the theoretically possible. It's a staggering engineering challenge, make no mistake, but it's no longer a violation of physics. A person could, in theory, be born on Earth, trained to be an astronaut, spend 44 years in flight, and arrive at Alpha Centauri in their old age. Or more likely, a young, carefully selected crew could be sent on a one-way mission of colonization. They would say goodbye to everyone they ever knew, to the entire Earth, forever, knowing they would live out their lives on the ship and their children would be the first to see the new sun rise over a new world. This is the concept of a generation ship, a vessel that is not just a ship, but a sealed world, a self-contained ecosystem hurtling through the void. It would have to be enormous, a floating city with farms, schools, water and air recycling systems, and a stable society capable of maintaining itself for decades without any hope of resupply or rescue. The social and psychological challenges are as daunting as the engineering ones. Could a community of a few hundred or thousand people remain healthy, sane, and purpose-driven for 44 years in the absolute blackness of interstellar space, with nothing outside their windows but the unmoving pinpricks of stars? They would be the most isolated humans in history, a tiny bubble of life surrounded by an infinite desert. But the 44-year timeline is also a bit of a trick, a simplification. It's the time from the perspective of us, the people left on Earth. We would watch the ship launch, and then we would wait, and wait. And 44 years later, we would get the signal that they had arrived. But for the crew on the ship, thanks to Einstein's special theory of relativity, time would actually be passing slightly more slowly. The faster you move through space, the slower you move through time relative to someone who is stationary. This isn't science fiction. It's a proven fact, confirmed by incredibly precise atomic clocks on airplanes and satellites. At 10% of light speed, this time dilation effect is very small, but it's there. For every 44 years that pass on Earth, about 43.8 years would pass on the ship. The crew would age about 3 months less than everyone back home. It's a tiny difference at this speed, but it's a hint of the strange time-warping effects that become dramatic as you go faster. It means that if we could go even faster, say 90% of light speed, the trip time from the crew's perspective could be cut down dramatically. A 44-year journey could feel like only 20 years to them. This is the other way to attack the problem of distance, not just by moving faster through space, but by bending time itself to make the journey feel shorter for the travelers. So achieving 10% of light speed isn't just about getting there quicker. It's the key that unlocks the door to the stars. It transforms an impossible journey into a monumental but conceivable undertaking. It's the difference between throwing a message in a bottle into the ocean and building a seafaring vessel to cross it. It's the first crucial step away from being prisoners of our solar system and toward becoming citizens of the galaxy. But as we'll soon see, generating that kind of speed requires not just a new engine, but a new way of thinking about energy itself. This is where physics, engineering, and imagination collide. The first and most obvious problem is propulsion. Our chemical rockets, the kind that took us to the moon, are useless for this. They are like trying to sail across the Pacific Ocean in a bathtub. They just don't have the efficiency or the power. We need entirely new ways to push ourselves through space. One of the most discussed and theoretically plausible concepts is nuclear propulsion. Not nuclear bombs, but controlled nuclear reactions. Imagine a reactor, much like on a nuclear submarine or aircraft carrier, but in space. It would heat a propellant, like liquid hydrogen, to tremendous temperatures and then blast it out of a nozzle to create thrust. This is called nuclear thermal propulsion. It could be maybe twice as efficient as our best chemical rockets. A step forward, but still not enough for star travel. So we need to go faster, much faster. We've talked about the need to reach a significant fraction of light speed, and that requires an energy source far beyond our chemical firecrackers. We need to harness a power that's truly stellar in nature. And in the mid-20th century, at the height of the atomic age, a group of the brightest and most daring minds in America asked a very simple, very terrifying question. What if we use the most powerful force we've ever unlocked as a propellant? This isn't about a controlled nuclear reactor, like on a submarine. This is far more direct, far more visceral. This is the concept of nuclear pulse propulsion, and it's exactly as crazy as it sounds. The idea, in its most breathtakingly bold form, is to propel a spacecraft by detonating nuclear bombs behind it. Seriously, you read that right. Not with a reactor, but with bombs. This wasn't just a sketch on a napkin. It was a seriously funded, deeply studied project called Orion, run by General Atomics in the late 1950s and early 1960s. And for a brief, glorious moment, it seemed like it might actually work. Let's unpack how this madness would operate. Imagine your spacecraft. It doesn't look like a sleek, needle-nosed rocket. It looks more like a massive, blunt-ended skyscraper or a colossal upright sewer pipe, because the business end is at the back. This is the pusher plate. It's a giant, circular slab of the toughest material we can imagine, probably a super alloy coated in something like graphite to handle insane heat. It's not just a plate, it's also a shield, because directly behind it is where the magic, or the mayhem, happens. The ship is loaded with thousands of small, specially designed nuclear devices. Think of them as atomic firecrackers. One by one, a mechanism would drop one of these bombs out of a hatch in the center of the pusher plate. It would fall just a short distance, maybe 100 meters or so. And then, bang, it detonates. Now, in the vacuum of space, a nuclear explosion doesn't create a fiery mushroom cloud like on Earth. There's no air to superheat and carry the debris. Instead, it creates an instantaneous expanding sphere of pure incandescent plasma, a sun-like fireball of subatomic particles and radiation moving at a tremendous fraction of light speed. This expanding ball of hellfire slams into the pusher plate. The force of that impact is unimaginable. It's like being hit by a tidal wave made of pure energy. The pusher plate, designed to absorb this stupendous blow, is kicked forward violently, and since the pusher plate is attached to the ship, the entire spacecraft is hurled forward. But wait, you might think, wouldn't that force just vaporize the plate? Turn it into molten slag? This is where the genius of the design comes in. The pusher plate isn't bolted directly to the main body of the ship. It's connected by the most heavy-duty shock absorbers ever conceived, a system of enormous pistons and dampeners. So, when the plasma wave hits, the plate itself is driven backward up these pistons, compressing them. The energy of the explosion is thus converted into a controlled mechanical push rather than a destructive shock wave. The plate might get incredibly hot, but it's designed to ablate, to shed its superheated surface layer like a lizard shedding its skin, which also helps to cool it. By the time the plate rebounds from its stroke, ready for the next push, the hot debris has dissipated into space behind it. Now you do this again. Drop, bang, push, and again. Drop, bang, push, and again. Every second or every few seconds, another atomic firecracker goes off. Bang, bang, bang. The ride wouldn't be smooth like a jetliner. It would be a constant, rhythmic, pounding acceleration. Thump, thump, thump. It would be like the world's most powerful jackhammer, firing at a rate that would slowly, inexorably build up speed. From the outside, it would look like a man trying to climb a cliff by repeatedly setting off dynamite in his hands and being blown upward by the blast. It is the absolute definition of brute force, and the calculations showed this brute force method could work astonishingly well. A full-scale Orion ship, a city block-sized behemoth, could theoretically reach speeds of 3, 5, even 10% of the speed of light. It could carry a payload the size of a small town, thousands of people, their supplies, entire ecosystems, making it a generation ship par excellence. The project's proponents dreamed of sending a fleet of these space battleships to Saturn by 1970. They weren't thinking small. But of course there are rather enormous buts. The first and most obvious is the launch. You can't possibly light this thing off from the surface of the Earth. The first few detonations would not only vaporize the launch pad, but would likely create a radioactive firestorm that would poison the atmosphere for miles around. The electromagnetic pulse from the blasts would fry electronics across a continent. The political and environmental nightmare of even testing such a system is unimaginable. The Project Orion team knew this. Their plan was to build the ship in orbit, using conventional rockets to lift the parts. The nuclear bombs would only be set off once they were far away from Earth, in the deep black where the fallout would harm no one. But that leads to the second, more subtle problem. The Partial Test Ban Treaty of 1963. This international agreement, a response to the very real fears of nuclear annihilation during the Cold War, prohibited the testing of nuclear weapons in the atmosphere, underwater, and in outer space. Setting off hundreds of nukes in space, even for peaceful purposes, would be a blatant and terrifying violation of this treaty. It would look to every other nation on Earth like a nuclear attack was underway. The potential for catastrophic misunderstanding was, and still is, far too great. So Project Orion was shelved, not because it was scientifically impossible. The physics, shockingly, is sound, but because it was politically and environmentally untenable. It was a product of its time, born in an era of atomic optimism and Cold War tension, when the power of the atom seemed to be the answer to every problem, even the problem of distance. Yet, the idea retains a certain gritty, compelling charm. It doesn't rely on magical materials or undiscovered physics. It uses a terrifying technology we already possess in a wildly novel way. It's the ultimate expression of, if you can't find a door, just use a cannon. It's the kind of solution a species might turn to if it were desperate, if it absolutely had to leave its solar system quickly and with a lot of baggage. It's not elegant, it's not clean, but it has a raw, honest power to it that more fanciful concepts lack. It's a reminder that sometimes the path to the stars might not be quiet and graceful, but loud, violent, and punctuated by the rhythmic thunder of man-made stars flaring into existence in our wake. Then there's the concept of fusion rockets. If we can ever achieve sustained, controlled fusion, harnessing the power that lights the stars, we could have an incredible energy source. A fusion rocket would work by shooting small pellets of fusion fuel, like deuterium and tritium, into a reaction chamber, igniting them with powerful lasers or magnetic fields, and then channeling the resulting superhot plasma out a magnetic nozzle to create thrust. The exhaust velocity could be a significant fraction of light speed, making the rocket incredibly efficient. Speeds of maybe 10–20% of light speed might be possible. This is one of our best bets for within the next millennium star travel. So we've talked about brute force, about literally throwing nuclear bombs out the back door, and also the clean fusion rockets to push us along. It's a wild, almost punk rock approach to space travel. But what if we could leave all that behind? What if we could move beyond mere explosions and tap into the pure, fundamental energy of creation itself? What if we could find the universe's ultimate battery? Well, according to physics, we already have. It's called antimatter, and it is, without a doubt, the most potent, the most efficient, the most terrifyingly perfect fuel source that reality allows. To understand antimatter, we first have to take a little detour into the heart of what everything is made of. You, me, this planet, the stars, we're all made of matter, the familiar stuff. Atoms with electrons whizzing around a nucleus of protons and neutrons. Now, for every type of matter particle, physics tells us there should be an opposite, a mirror image, a twin born with opposite properties. For the electron, there's the positron, identical in mass, but with a positive charge instead of a negative one. For the proton, there's the antiproton, negative instead of positive. This is antimatter. It's not some magical substance from a story. It's a real, predicted, and observed part of the universe. It's the ultimate example of cosmic symmetry. For every yin, there is a yang. And when this yang meets its yin, when matter and antimatter meet, they don't just react like chemicals. They don't combine or explode in a conventional sense. They perform the ultimate vanishing act. They annihilate each other. Poof. In a flash of energy, they cease to be matter entirely. 100% of their mass is converted into pure energy, according to the most famous equation in the world, EMC square. Let's unpack that for a second, because we throw that equation around a lot without feeling its weight. E is energy. M is mass. C is the speed of light. And the speed of light is a huge number, but c square is that number multiplied by itself. It is an astronomically enormous number. This means that a tiny, tiny amount of mass is equivalent to a colossal, mind-boggling amount of energy. It's the reason the sun can shine for billions of years, fusing a tiny fraction of its mass into energy. But even the sun's fusion process is inefficient. It only converts about 0.7% of the mass involved into energy. Matter-antimatter annihilation is 100% efficient. It is the universe's gold standard for energy production. To give you a sense of scale, let's play with some numbers. The space shuttle's enormous. Rust-colored external fuel tank held over 700,000 kilograms of liquid oxygen and hydrogen. The energy released by burning all that propellant is what lifted the shuttle into orbit. Now, how much antimatter would it take to release the same amount of energy? Are you ready for this? About 10 grams. A single paperclip weighs about a gram. You could hold the equivalent energy of a space shuttle launch in the palm of your hand. A few hundred grams of antimatter could theoretically provide enough energy to send a large crewed ship on a tour of the entire solar system. A few kilograms could be enough for an interstellar journey. This is power on a scale that redefines what's possible. So how would an antimatter rocket work? It wouldn't be about annihilation directly creating thrust. That would be a beam of pure radiation shooting out the back, which is incredibly energetic, but doesn't provide much push in the conventional sense. Instead, the most practical design is what's known as an antimatter-initiated fusion rocket. Imagine a robust reaction chamber at the stern of the ship. Inside, you have a pellet of fusion fuel, like deuterium and helium-3. Then, you inject a tiny, precisely metered amount of antimatter, a few billionths of a gram perhaps, into the center of this pellet. The instant the antimatter contacts the matter in the pellet, it annihilates. This isn't a slow burn. It's an instantaneous, microscopic star being born and dying in a nanosecond. The energy released is so intense, so ferociously hot, that it triggers a fusion reaction in the surrounding fuel, just like the heart of a star. This creates a superheated plasma, an ionized gas with temperatures in the millions of degrees. This plasma, now expanding violently, is then channeled and directed out of a magnetic nozzle. Because the plasma is electrically charged, powerful magnets can squeeze it and shoot it out the back like a blowtorch, pushing the ship forward. The antimatter is merely the match. The fusion plasma is the bonfire it lights. The efficiency of this process is off the charts. The exhaust velocity, the speed at which the propellant is flung out the back, could be a significant fraction of light speed itself. Remember the tyranny of the rocket equation? The faster you can throw your exhaust out, the less propellant you need to get a push. With an antimatter-driven exhaust velocity, you could achieve constant, powerful acceleration for months or years, potentially reaching 50, 60, even 90% of light speed. The journey to Alpha Centauri could shrink from millennia to years, from a multi-generational odyssey to a single mission. This is the game changer. This is the technology that could truly open the galaxy. But, and this is a but so massive, it could have its own gravitational field. There are monumental, perhaps even show-stopping, problems. We've been talking about grams of antimatter as if it's something you can just pick up at a cosmic gas station. It is not. First, production. Antimatter is incredibly difficult to make. We currently produce it in particle accelerators, like CERN. They smash particles together at near-light speeds, and in the energy of those collisions, particle-antiparticle pairs are created. We can then use magnetic fields to separate and trap the antimatter. The current rate of production is humble. We measure it in atoms. We might produce a few billion antiprotons in an experiment. A billion antiprotons sound like a lot, but it has a mass of about 1.6 trillionths of a gram. To make a single gram of antimatter, we would need to scale up our current production rate by many, many orders of magnitude. The energy required to produce it, with our current hopelessly inefficient methods, would be staggering. It's been estimated that with today's technology, producing a single gram of antimatter could cost trillions of dollars and consume more energy than a large nation uses in a year. We wouldn't be fueling a starship, we'd be bankrupting planets. Second, storage. This is the real nightmare. Antimatter cannot touch matter, not even a little bit. If a single atom of it touches the wall of its container, it annihilates. So how do you store it? You use a device called a penning trap. It's a miniature, incredibly precise prison made of magnetic and electric fields. The antimatter particles, which are electrically charged, are suspended in a perfect vacuum in the center of this trap, held away from all matter by these invisible force fields. It's like trying to hold a single hyperactive dust mote in midair using only a dozen carefully aimed hairdryers. It requires immense precision and constant flawless power. Any failure, any fluctuation, any tiny error, and your fuel supply instantly transforms into a bomb. Storing a gram of antimatter would be like holding a thermonuclear weapon. That could go off if the power ever flickered. The idea of keeping kilograms of it on a spacecraft is the stuff of heart attacks for engineers. So while the physics of an antimatter rocket is sound, the engineering and economics are, for now, pure fantasy. It represents a level of technological control over nature that we can barely imagine. It would require a civilization that has mastered energy production on a planetary scale, perhaps one that has built a Dyson swarm around the sun to power its antimatter factories. It is the fuel of a Type II civilization on the Kardashev scale, a species that has become the master of its solar system, not just a visitor. Yet it captures the imagination like nothing else. It is the ultimate fuel, the end point of propulsion technology. If we ever hear that a ship named Prometheus or Icarus is launching with an antimatter drive, we will know that humanity has truly come of age in the cosmos. We will have learned to bottle lightning, to harness the very fire of existence to push us into the great dark. It is a dream, a powerful, radiant dream of what we might one day become. Now, all these methods, nuclear, fusion, antimatter, rely on the same basic principle. You are carrying your fuel with you. This is the tyranny of the rocket equation, a cruel and unforgiving master for any spacecraft designer. It states that to go faster, you need more fuel. But more fuel makes your spacecraft heavier, which means you need even more fuel to push that heavier craft, which makes it heavier still, and so on. It leads to an exponential growth in the mass of your spacecraft. To get even a small probe to a nearby star in a reasonable time, you might need a fuel tank larger than the Empire State Building. It's a vicious cycle that seems to put star travel forever out of reach. So we need to think outside the box. What if we didn't carry our fuel? What if we could scoop it up as we go? This is the idea behind the Bussard ramjet, a brilliant concept proposed by physicist Robert Bussard in 1960. Imagine a starship with a gigantic electromagnetic scoop hundreds of kilometers wide on its front. As it moves through space, it scoops up the tiny stray atoms of hydrogen that float in the interstellar medium, only a few atoms per cubic centimeter. But if your scoop is big enough and you're going fast enough, you can collect a meaningful amount. This hydrogen would then be funneled into a fusion reactor, used as fuel, and blasted out the back for thrust. It's like a jet engine for space. The beauty is that you don't carry fuel. You become a self-sustaining engine. In theory, a ramjet could accelerate for years, eventually reaching relativistic speeds, a significant fraction of light speed. The problem? The interstellar medium is very, very thin. The scoop would have to be astronomically large to collect enough hydrogen, and the magnetic fields required would be immense. Furthermore, at high speeds, the collected hydrogen would be hitting the scoop like a torrent of cosmic radiation, creating huge drag and technical challenges. It's a beautiful idea, but one that may be more practical in the pages of a novel than in reality. Perhaps the most elegant and seemingly magical solution is to leave the engine behind altogether. This is the concept of the light sail. Instead of pushing yourself with expelled fuel, you let yourself be pushed by light. Photons, the particles of light, may have no mass, but they have momentum. When they bounce off a surface, they give it a tiny, tiny push. It's negligible on Earth, but in the frictionless vacuum of space, a constant push can lead to incredible speeds over time. We could build a gigantic, ultra-thin, and reflective sail, perhaps kilometers across. Then, we would point an incredibly powerful laser, or an array of lasers, from somewhere in the solar system, like orbiting the sun, at this sail. The constant pressure from this laser beam would push the sail, and the spacecraft attached to it, faster and faster. Since the laser beam doesn't diverge much, it could keep pushing the craft for a long, long way. Projects like Breakthrough Starshot are seriously investigating this for sending tiny, gram-weight probes to Alpha Centauri within a few decades. They would be pushed by a giant Earth-based laser to 20% the speed of light, arriving in about 20 years. For a crewed ship, the sail and the laser would need to be unimaginably larger, but the principle is sound. It's a beamed energy propulsion system, and it's one of the most promising concepts for fast interstellar travel. Okay, so let's assume we've cracked it. Through some miracle of future engineering, be it a compact fusion drive, a massive light sail, or a trickle of antimatter, we have built a starship capable of 10% of light speed. We name it the SS Ambition. We point it at Alpha Centauri, and we go. The journey itself, even at this fantastic speed, would take over 44 years. This introduces our next great challenge: time. Who goes on a 44-year journey? It's longer than most careers. You'd be saying goodbye to everyone and everything you ever knew on Earth, forever. This would have to be a one-way trip for colonization, or the crew would have to find a way to survive the 88-year round trip. This brings us to the concepts of generation ships, or hibernation. A generation ship is exactly what it sounds like: a gigantic, self-contained ark. It's not just a ship, it's a mobile world. It would have to contain entire ecosystems, farms for food, water, and air recycling systems, schools, hospitals, everything needed to sustain a human population for centuries. The crew that leaves Earth would not be the crew that arrives. Their children, or even their grandchildren, would be the ones to finally reach the destination. The social and psychological challenges are immense. Could a closed society remain stable and sane for generations in the empty blackness of space? Would they even remember or care about the mission their great-grandparents started? They might come to see the ship itself as their entire universe. It's a fascinating and terrifying prospect. The other option is to put the crew to sleep. Science fiction has made suspended animation or cryogenic hibernation a staple. The idea is to drastically lower the body's metabolism, slowing life to a near standstill, so that decades pass like moments for the sleeper. Bears hibernate. Some frogs can freeze solid and thaw out later. Could we do that to humans? We are a long, long way from that technology. The process of freezing creates ice crystals that shred cell membranes. We'd need to perfect some form of vitrification, turning tissues into a glass-like state without ice. Even if we could safely put someone under, keeping them stable and healthy for decades, and then safely reviving them, is a medical mountain we haven't even begun to climb. But it remains a compelling idea to circumvent the problem of time. There's another, even weirder aspect of time to consider when traveling at a significant fraction of light speed: time dilation. This is not science fiction. It's a proven cornerstone of Einstein's theory of relativity. The faster you move through space, the slower you move through time relative to someone who is stationary. Let's say our ship, the SS Ambition, is traveling to a star 10 light years away at 90% the speed of light. For us on Earth, watching on a giant clock, the journey would take just over 11 years one way. But for the crew on the ship, because of their incredible speed, time would be passing more slowly. Their clocks, their heartbeats, their aging would all be slowed down. From their perspective, the trip might only take about 5 years. They would age 5 years while everyone on Earth aged 11. This effect becomes more extreme the closer you get to light speed. On a truly relativistic journey to the center of the galaxy and back, the crew might only age decades, while tens of thousands of years passed on Earth. They would return to a planet they no longer recognized. This solves the problem of crew longevity on long journeys, but it creates a profound existential loneliness. You are not just leaving your home, you are leaving your entire epoch. So, we've imagined ways to travel to another star, a monumental achievement to be sure, but that's just the first step. Our goal is to leave the galaxy. To do that, we need to understand the structure of our Milky Way. We don't live in a flat, featureless disk. Our galaxy is a barred spiral with major arms: Perseus, Sagittarius, Norma, Scutum Centaurus, and minor ones like our own Orion Spur. The Sun is located about 27,000 light-years from the supermassive black hole at the galactic center, Sagittarius A star. The disk of the galaxy is about 1,000 light-years thick on average, and we are roughly in the middle of that thickness. To leave the galaxy, we have two main choices: go up or down out of the galactic plane, or go outward through the disk towards the outer halo. The nearest edge of the galactic disk is, well, it's not a sharp edge. The density of stars just gradually decreases. But if we define the edge as where the star density drops off dramatically, we're talking about traveling from our position, roughly 27,000 light-years from the center, to maybe 50,000 or 60,000 light-years out. That's a journey of at least 23,000 light-years minimum just to get to the sparse outer fringe. Alternatively, we could try to go perpendicular to the disk. To get completely clear of the bulk of the galactic mass, we'd need to travel about 1,000 light-years up or down. Let's let that sink in. Our earlier heroic journey was to Alpha Centauri at 437 light-years. Now we're talking about distances of thousands of light-years. At our hopeful 10% of light speed, a 1,000 light-year journey up would take 10,000 years of ship time. And because of time dilation at that speed, it would still be 10,000 years for the crew. A journey to the outer edge, 23,000 light-years away, would take 230,000 years. These are not journeys. These are epochs. They span timescales longer than modern Homo sapiens has existed. This is why leaving the galaxy is in a completely different league of difficulty than merely visiting another star. The energy required for such a journey is beyond apocalyptic. It would require the total energy output of a star, harnessed and controlled by a civilization of gods. This brings us to the concept of the Kardashev scale, a way of measuring a civilization's technological advancement based on energy use. A Type 1 civilization can use all the energy available on its home planet. We are not quite there yet. We're about a Type 0.7. A Type 2 civilization can harness the entire energy output of its star, for example, by building a Dyson sphere, a megastructure encapsulating the sun to capture its light. A Type 3 civilization can control the energy of an entire galaxy. To even contemplate a mission to leave the galaxy, we would likely need to be a solid Type 2 civilization, masters of stellar energy. How would a Type 2 civilization approach this? Their ships wouldn't be the cramped vessels we imagine. They would be world ships, planetoids engineered for travel, or fleets of ships the size of continents. Their propulsion might not be rockets at all, but something even more exotic. Perhaps they would have mastered gravity control. If we could find a way to manipulate gravity to create a repulsive force against the fabric of space-time itself, we could potentially fall towards our destination without needing reaction mass. This is the idea behind the hypothetical warp drive of science fiction. While purely speculative, it's fun to explore within the bounds of theoretical physics. The closest thing to a warp drive in real physics comes from the work of Miguel Alcubierre in 1994. He proposed a mathematical model where a spacecraft could be enclosed in a warp bubble. In front of the bubble, space-time itself would be compressed. Behind the bubble, space-time would be expanded. The ship inside this bubble would itself be motionless in its local space. It's the space around it that is moving. This gets around the universal speed limit because the ship isn't moving through space faster than light. Space itself is moving around the ship. Think of it like a surfboard on a wave. The surfboard isn't moving through the water. The wave is carrying it. In this analogy, the wave is a distortion of space-time. The catch? To create this distortion, you need something with negative mass or negative energy density to twist space-time in the required way. Does such exotic matter exist? We have hints in quantum physics, like the Casimir effect, which shows negative energy densities can exist in a limited way. But the amounts needed for an Alcubierre drive are astronomical, perhaps requiring the mass energy of entire Jupiter-sized planets. It also has other nasty potential side effects, like building up a wall of high-energy particles at the front of the bubble that would vaporize your destination upon arrival. It's a fascinating thought experiment that shows us how space-time might be manipulated, but it is firmly in the realm of mathematical possibility, not engineering reality. Perhaps a more plausible, yet still incredibly far future technology for galactic travel would be the creation of a network of wormholes. A wormhole is a hypothetical tunnel through space-time, a shortcut connecting two distant points. You go in one end and pop out the other, maybe thousands of light years away. Again, the math and general relativity allows for such structures. But like the warp drive, they would require exotic matter to prop them open and prevent them from collapsing instantly. If a future civilization could stabilize wormholes, they could create a subway system for the galaxy. To leave the galaxy, you'd simply find a wormhole that had its other end out in the intergalactic void. But creating such a thing, or finding a natural one, is the stuff of cosmic fantasy for now. Let's assume we've become a Type 2 civilization. We've built a Dyson sphere around our sun, and we're harnessing nearly all of its energy output. We decide to build a vessel, an arc of arcs, to send a seed of humanity out of the Milky Way. What would the journey be like once we finally push away from the familiar spiral arms? The first thing we'd notice as we travel outward is the changing sky. The stars, which from Earth are a dense, glorious tapestry, would begin to thin out. The constellations would distort and melt away over the centuries. The Milky Way, that glorious river of light that has guided and inspired humans for all of history, would slowly shrink from a broad band into a faint, localized smudge behind us. We would watch our home galaxy recede, becoming just another island universe in the Black Sea. Ahead, there would be almost nothing. A few lonely ancient stars of the galactic halo, and the faint fuzzy blobs of other galaxies, trillions of kilometers away. The blackness would be deeper, more absolute than any human had ever experienced. The sense of isolation would be terrifying and profound. And what would we find out there, in the intergalactic void? It is not a complete vacuum. It contains a few atoms per cubic meter, compared to the few atoms per cubic centimeter in interstellar space. It is a desert compared to the ocean of the galaxy. There would also be dark matter, the mysterious, invisible stuff that makes up most of the galaxy's mass and extends far beyond the visible stars. We wouldn't be able to see it or feel it, but its gravitational pull would still be there. There might also be rogue planets, worlds flung from their star systems during cosmic collisions, now drifting forever in the darkness, frozen and dead. Perhaps our ark ship could use one of these as a resource, mining it for water and minerals. The ultimate goal? Perhaps to reach another galaxy. The nearest major one is the Andromeda Galaxy, a beautiful spiral even larger than our own. It is 2.5 million light-years away. At 10% of light speed, the journey would take 25 million years. This is so far beyond human comprehension that it ceases to be a journey and becomes an act of biological destiny. The only way such a trip could be contemplated is with a completely self-sufficient world ship, with a society utterly dedicated to this single multi-million-year purpose, or with a crew in some form of perfect, eternal hibernation. Or, of course, with that mythical warp drive, making the trip perhaps manageable in a human lifetime from the crew's perspective. But here's a thrilling cosmic thought. We don't necessarily need to go to another galaxy. The Milky Way and Andromeda are on a collision course. In about 4 to 5 billion years, they will begin to merge into a new, larger galaxy, often called Milky Way. The dance will take billions of years. Stars are so far apart that actual collisions will be rare. The two galaxies will mostly pass through each other, their gravity pulling and twisting them into a new elliptical shape. So, in a way, if we just stay put, our distant descendants will witness a galactic merger. They will, in effect, experience a new galactic environment without ever having to leave home. But that's cheating for our question of leaving. As we push our thought experiment to its limits, we must confront the deepest questions of all. Why? Why would we ever attempt such a thing? The energy cost is unimaginable. The timescales are geological. The risks are infinite. The motivation would have to be equally powerful. Perhaps it is the ultimate insurance policy. Some cataclysm could make the galaxy uninhabitable. A wave of gamma-ray bursts from merging neutron stars, the awakening of the supermassive black hole at the center, or even the eventual death of all stars. Sending arcs out into the void would be a way to ensure that the spark of consciousness, the story of humanity, never completely dies. Or perhaps it is simply because it is there. The same insatiable curiosity that made us paddle across oceans, climb the highest peaks, and journey to the moon might, millions of years from now, compel us to see what lies beyond the shores of our galactic island. It is the final frontier, not just of space, but of time, energy, and life itself. So, can we leave our Milky Way galaxy? Today, with our chemical rockets and our fragile bodies, the answer is a gentle but certain no. It is a dream woven from the threads of distant possibility. But the universe is old, and we are young. We have barely taken our first steps. The laws of physics, as we understand them, do not explicitly forbid it. They just demand a price so high it seems mythical. They demand that we evolve, not just biologically, but technologically and as a civilization. They demand that we become masters of energy and time. They demand that we become, for all intents and purposes, a different kind of species altogether. The journey to the stars and beyond them is not a journey of distance. It is a journey of the mind. It is a test of our ingenuity, our patience, and our courage. It asks us if we can think in scales of centuries and millennia, not just fiscal quarters. It asks if we can cooperate as a planet to achieve a goal whose payoff none of us will ever see. The voyage out of the galaxy may never happen, but in asking the question, in daring to dream the blueprint, we are already stretching the boundaries of what it means to be human. We are reaching, once again, for the stars, and in doing so, we are reminding ourselves that the most powerful engine for any journey is not found in a reactor core, but in the boundless, hopeful, and curious human spirit. And that, perhaps, is the most important destination of all. Good night. Have a deep sleep. Hello, my friends, and welcome to Hafi Sleep. Whether you're tuning in from a bustling city just winding down, a quiet town deep in the night, or somewhere halfway across the globe where the sun is still high, we're so glad you're here. Tonight, we're going on a journey unlike any other. A journey across space and time to the very heart of our home in the cosmos, the Milky Way Galaxy. So find your coziest spot, settle in, and let your imagination drift among the stars. If this sounds like the kind of escape you love, don't forget to subscribe to Hafi Sleep and hit that like button. It truly helps our little channel grow. And we'd love to know, where in the world are you watching from, and what time is it for you? Drop a comment below and share your moment with us. Now, close your eyes, take a deep breath, and let's begin. Imagine, for a moment, that you are standing on a quiet hilltop on a perfectly clear, moonless night. Far from the glare of city lights, you look up, and there, arching across the heavens like a ghostly river of spilled diamonds, is a sight that has captivated every human civilization since the dawn of our species: the Milky Way. It is a breathtaking, almost mystical spectacle. But what you are truly seeing with your own eyes is the collective glow of hundreds of billions of stars, the very structure of our home galaxy, seen from within. You are not just looking at a beautiful sight. You're looking at your own city, your own neighborhood, on a scale so immense it defies everyday comprehension. This, right here, is our galactic address. And for this journey, you don't need a telescope or a spaceship. All you need is your curiosity. So, get comfortable, and let's embark on an epic voyage of exploration. Let's unravel the story of our Milky Way. Our story begins not in a specific place, but in a specific time. A time before the Earth, before the Sun, before even the Milky Way itself existed. We have to rewind the cosmic clock back over 13 billion years to a point just a few 100 million years after the Big Bang itself. So let's settle in and really picture this moment, this cosmic dawn. Imagine the universe as a vast, dark, and incredibly simple soup. The main ingredients? Just two: hydrogen and helium. That's it. After the colossal fireball of the Big Bang had expanded and cooled for a few 100 million years, this was what was left. A thin, foggy broth of these two simplest gases, stretching out in every direction for distances so immense they are almost impossible to fathom. There were no landmarks, no stars to navigate by, no light at all, in fact, except for the faint, fading afterglow of the birth of the universe itself. which by this time had cooled to a uniform, invisible microwave whisper. It was a profoundly dark and quiet place, but it was not perfectly uniform. This is the most crucial part of the whole story. You see, that primordial soup had tiny, tiny ripples in it. Imagine the surface of a perfectly still pond, and then a single tiny raindrop falls, creating the faintest of ripples that spread out. Now imagine those ripples are frozen into the fabric of space itself. These imperfections, these slight variations in density, some patches were just a tiny, tiny bit thicker than others, were the seeds of everything to come. They were the cosmic blueprints imprinted by the wild physics of the Big Bang. Without these tiny fluctuations, gravity would have had nothing to grab onto. The universe would have remained a forever expanding, perfectly smooth and utterly boring sea of gas. There would be no us, no stars, no galaxies, no story to tell. So these tiny ripples are the reason we are here today, talking about this. It's a humbling thought.
Now, enter the main character of our story, gravity. Gravity is the ultimate slow and steady winner. It is the most patient force in the universe. It doesn't need to be flashy, it just is. And it never, ever stops working. Its rule is simple. Anything that has mass attracts any other thing that has mass. The more mass you have, and the closer you are, the stronger the pull. So gravity looked out across this vast, rippled sea of gas and saw opportunity. Those slightly denser patches, those cosmic overdensities, had just a little bit more gravity than the less dense areas around them. So ever so slowly, over millions of years, gravity began to pull the gas from the thinner areas toward the thicker areas. It was a cosmic gathering, a gentle pulling together of material. Think of it like this. If you have a stretchy sheet and you place a single heavy marble in the center, it will create a dip. If you then scatter tiny ball bearings across the sheet, they will all naturally roll inward toward the marble. In our early universe, the slightly denser patches of gas were like that marble, creating a tiny gravitational dip in the fabric of space-time itself. The surrounding gas was like the ball bearings, slowly, inevitably, drifting inward. As more and more gas gathered into these pockets, they became even denser, which made their gravitational pull even stronger, which attracted even more gas. This is what scientists call a runaway process, a positive feedback loop. The growth started imperceptibly slow, but it began to snowball over time. These gathering clouds of gas were unimaginably huge. We're talking about clouds that could be hundreds of thousands of light years across. To put that in perspective, a single light year is about 6 trillion miles. So these were behemoths on a scale that truly defies human comprehension. They were the primordial raw material, the cosmic lumber yards, from which entire galaxies would eventually be built. And as these vast clouds collapsed under their own immense weight, something interesting started to happen. They didn't just collapse into one single giant object. They became unstable. The cloud would start to ripple and churn from within. And much like a mist condensing into individual droplets of water, these giant gas clouds would fragment and break apart into smaller, dense clumps. Each of these smaller, collapsing clumps was destined for a spectacular future. Each one was a star in the making, a protostar. And because these clouds were so enormous, they gave birth to thousands, even millions, of these protostars all at once, creating the first ever star clusters in the universe. Now here's where things get really interesting. This first generation of stars, often called population 3 stars by astronomers, a bit of a boring name for such fascinating objects, were nothing like the stars we see in our night sky today. They were the true titans, the leviathans of the cosmos. They had a pure diet of only hydrogen and helium. There were no heavier elements available to them yet, and they formed from these massive, pristine clouds. Without metals, which is what astronomers call any element heavier than helium, to help cool the gas and allow it to fragment more easily. The clumps that formed had to be much, much bigger to begin the process of collapse. So these first stars were monsters. They weren't just a little bigger than our sun. They were colossal. Many of them were between 100 and 1,000 times more massive than our sun. Can you imagine a star that size? Our sun is already so huge that over 1 million Earths could fit inside it. These stars were on another level entirely. And with immense size comes immense gravity. The gravity at the core of one of these behemoths was absolutely crushing. This created unimaginable pressure and heat. The core temperatures of these stars would have been scorching, many times hotter than the core of our sun. This extreme environment meant that these stars lived their lives at a breakneck pace. A star like our sun is a model of efficiency and longevity. It has been burning steadily for 4.6 billion years and has about 5 billion more to go. It's a long-distance runner. These first massive stars were the ultimate sprinters. They burned through their vast reserves of hydrogen fuel in a frantic race that lasted only a few million years. In cosmic terms, that's not even a blink of an eye. It's a fleeting instant. They shone with a fierce, intense blue-white light that would have been terrifying and beautiful to behold. But this furious burning couldn't last. When such a massive star runs out of hydrogen fuel in its core, the balance of its life is over. The outward pressure from nuclear fusion that had been holding up the star against the immense inward pull of gravity suddenly drops. And gravity, always waiting, always patient, wins in an instant. The core collapses catastrophically. In a matter of seconds, the star's inner core, which might be several times the mass of our entire sun, is crushed into a sphere only a few dozen miles across. The shock wave from this sudden violent collapse ripples outward through the entire star, and the outer layers rebound off the incredibly dense core and are blasted out into space in one of the most energetic events in the entire universe, a supernova explosion. The death of these first stars was not an end. It was a magnificent, violent, and creative beginning. The ferocious energy of a supernova is so great that it acts as a cosmic forge. In those final, incredible moments of heat and pressure, the simple atoms of hydrogen and helium are smashed together to form brand new, heavier elements. In the heart of the explosion, nuclear fusion happens at an incredible rate, creating carbon, oxygen, nitrogen, silicon, and iron, all the way up the periodic table. For the very first time, the universe was no longer just hydrogen and helium. It was being seeded with the building blocks of everything else. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was first created in the heart of a star that died billions of years ago. We are, literally, made of stardust. And these supernovae didn't just create these elements. They blasted them out across space at nearly the speed of light. They took the precious, newly forged metals and scattered them throughout the surrounding gas clouds, polluting the pristine cosmic soup. This was the most important recycling program in history. The universe was no longer pure and simple. It was now enriched, complex, and ready for the next act. This newly enriched gas, now containing all the ingredients for rocks, for planets, and for life, would now collapse to form the next generation of stars. But this time, because the gas contained these heavier elements that could help it cool and fragment more efficiently. The stars that formed could be a wider variety of sizes, including smaller, longer-lived stars like our Sun. This changes everything. Before this pollution, the universe was a simple place. Now it's chemically complex. This enriched gas is now like a soup that's had all the vegetables, herbs, and spices added to it. It's no longer just a bland broth. And this seasoned soup is now the raw material for the next generation of stars. But this time, the star-making process is different. Those new heavy elements, particularly dust grains made of carbon and silicon, are incredibly efficient at cooling down the gas clouds. Cooler gas can clump together more easily, and it can fragment into smaller, denser knots. This means that from this enriched gas, you don't just get behemoth stars. You can also form smaller, more stable stars, like our own Sun, stars that can burn for billions of years, providing a stable energy source for any planets that might form around them. Now gravity, our patient architect, sees all this new, enriched, and now cooling gas and gets back to work. But its job description has just expanded. It's no longer just pulling together gas to form individual stars. It starts pulling together everything. Those first generations of stars, both the giants that went supernova and the smaller ones that lived longer, weren't born in isolation. They were born in clusters. Gravity begins to pull these star clusters together. It pulls together the massive clouds of now enriched gas. It pulls together the dark matter that we now know is also there, providing an invisible scaffolding. All of these things, star clusters, gas clouds, dark matter, begin to orbit a common center of gravity. And here's where physics does its beautiful dance. As this large, loosely organized swarm of stuff collapses inward, a wonderful thing happens. It begins to spin, and it naturally starts to flatten out. You can see this principle right in your own home. Think of a pizza chef tossing a spinning ball of dough into the air. As it spins, it flattens out into a disc. Or think of a figure skater pulling their arms in during a spin. They spin faster. This is conservation of angular momentum, a fundamental law of the universe. The same thing happened to our infant Milky Way. All the tiny random motions of the gas clouds and star clusters, as they were pulled together, averaged out into one general direction of spin. As everything collapsed inward, that spin accelerated and forced the material to form a vast rotating disk. The central region became a bulging sphere, the galactic bulge, while the outer material settled into the spinning disk we see today. This whole process didn't happen neatly or cleanly. Our galaxy wasn't built like a skyscraper from the ground up with a single blueprint. It was built through a process called hierarchical assembly, which is a fancy term for mergers and acquisitions. Imagine it as a cosmic game of Pac-Man. The early universe was full of small, dwarf, galaxy-sized clumps of stars and gas. Gravity pulled them toward each other. They merged, creating a larger structure. That larger structure then merged with other similar-sized structures. Over billions of years, through a series of these mergers, our majestic spiral galaxy was assembled piece by piece. It's a messy, violent, and slow process, but it's how all the big galaxies in the universe we see today were built. We can even see the fossilized evidence of this in our own galaxy. Streams of stars orbiting in the galactic halo, which are the torn-apart remains of smaller galaxies that were consumed by the growing Milky Way long, long ago. So, from the violent, creative deaths of the first stars, the stage was set not just for new stars, but for the grand architecture of galaxies themselves, our Milky Way being one magnificent example. So, let's picture our galaxy not as the elegant, stately spiral we often imagine, but as a toddler, a cosmic toddler, full of energy, chaos, and a habit of grabbing anything nearby and pulling it into its orbit. This young Milky Way was a far cry from the relatively orderly system we call home today. It was a wild place, a gravitational battlefield where the rules were simple. The biggest bully wins, and our galaxy was quickly becoming the biggest bully in our particular neighborhood. This process is what astronomers, with a delightful lack of PR concern, call galactic cannibalism. It's a stark term, but it's perfectly accurate. The Milky Way grew its immense size not just by gently gathering loose gas, but by quite literally eating smaller galaxies that ventured too close. Gravity is an irresistible force, and if a tiny dwarf galaxy, containing perhaps only a few 100 million stars, found its path taking it near the burgeoning Milky Way, it was all over. The Milky Way's immense gravitational pull would seize it, stretching it, tearing it apart, and eventually digesting it, adding the smaller galaxy's stars, gas, and dark matter to its own growing body. And the most amazing part? This isn't just ancient history. It's happening right now. Our galaxy is still accreting, still consuming. We have several small satellite galaxies, like the large and small Magellanic Clouds, orbiting us right now. They are currently being pulled in, and billions of years from now, they too will be assimilated, becoming part of the Milky Way's extended halo. But we can also see the ghosts of mergers past. When a small galaxy is torn apart, it doesn't just vanish instantly. Its stars are stripped away in long, flowing streams that continue to orbit the Milky Way's center. These are like cosmic breadcrumbs, or more accurately, like the lingering swirls in a cup of coffee after you've stirred in the cream. They are tidal streams, and astronomers, with their powerful telescopes and sky-surveying missions, can actually map these faint, ethereal rivers of stars. They are the fossilized evidence of ancient acts of cosmic consumption, the galactic equivalent of finding dinosaur bones in your backyard. One of the most dramatic of these ancient mergers has been nicknamed the Gaia sausage. Now, that might sound like something you'd order at a space-themed diner, but it's actually a fascinating discovery named for the European Space Agency's Gaia mission. The Gaia spacecraft is one of the most ambitious projects in astronomy. It's not just taking pictures of stars, it's meticulously mapping the precise positions, distances, and most importantly, motions of over 1 billion stars in our galaxy. It's like giving the Milky Way its first ever comprehensive census, and then making a movie of how everyone is moving. By analyzing this incredible trove of data, astronomers noticed something strange. A large group of stars in the inner halo of our galaxy weren't moving in random orbits. They were all moving in very radial, elongated orbits, like comets diving in toward the sun and then swinging back out. But the key was this: they were all doing it together, and their paths were all pointed in roughly the same directions. This was a telltale signature. It was the ghost of a dwarf galaxy that didn't just gently merge with us side on. About 10 billion years ago, this unfortunate galaxy, which scientists now call the Gaia Sausage Enceladus Galaxy, came screaming in for a head-on collision. It was a cosmic car crash of epic proportions. This violent merger didn't just add stars to the Milky Way, it fundamentally reshaped it. The energy of the impact likely helped to puff up and thicken the nascent galactic disk, contributing to the thicker disk we see today. It was a pivotal moment in our galaxy's adolescence, a growth spurt triggered by a dramatic event the evidence for which is still written in the paths of the stars it left behind. It's a history book written not in words, but in motion. Now, while all this chaotic merging was happening on the outside, something else was happening on the inside. All that gas and dust and all those stars being pulled together were, as we mentioned, starting to spin. And as they spun, they began to flatten out. This is a fundamental principle of physics. Think about that pizza chef again. They start with a ball of dough. As they spin it, the centrifugal force pushes the dough outward, and it naturally flattens into a wide, thin disk. The same thing happened to our galaxy. The random churning motions of the early cloud began to average out into one dominant direction of rotation. As everything collapsed inward, this spin accelerated, forcing the material into a frisbee-like shape. This is how the beautiful galactic disk we know today began to form. But at the very center of all this collapsing, spinning chaos, things were getting extremely intense. Imagine a crowded dance floor where everyone is moving toward the center. It gets incredibly packed. In the heart of the young Milky Way, an immense amount of mass, gas, dust, and stars was piling up into a relatively tiny space. The gravity in this region became unimaginably strong. Scientists believe that it was here, in this ultra-dense environment, that a supermassive black hole was born. It likely started as a smaller black hole, perhaps from the death of a massive early star, and then grew insatiably by feeding on the plentiful gas and even entire stars that were unlucky enough to wander too close. It gorged itself, becoming the monstrous gravitational anchor we now call Sagittarius A. It's been sitting at the heart of our galaxy, a silent, dark king on its throne for almost the entire history of the Milky Way. Meanwhile, out in the newly forming disk, the conditions were becoming perfect for a new chapter. The gas here was now rich and complex, seasoned with all those heavy elements from countless supernovae. This enriched gas was far better at cooling down and clumping together than the pristine hydrogen and helium of the early universe. And so, a new, more diverse generation of stars began to ignite. These were stars like our sun, not too big, not too small, stable, and long-lasting. And because they formed from this chemically rich soup, something new and wonderful could happen around them: the formation of rocky planets. The heavy elements like iron, silicon, and oxygen could clump together to form dust grains, then rocks, then planetesimals, and finally, full-fledged planets. The stage was now set for worlds with solid surfaces, with minerals, with chemistry complex enough to potentially brew the ingredients for life. Our sun is a proud member of this later generation. It is a child of the Milky Way, born roughly 4.6 billion years ago from a cloud of gas that had been recycled through multiple generations of stars that lived and died long before it. Every single atom in your body that is not hydrogen or helium, the carbon in your cells, the nitrogen in your DNA, the oxygen in your lungs, the iron-carrying energy in your blood, was forged in the nuclear furnace of a star that died before our sun was born. That star ended its life in a spectacular supernova explosion, scattering these newly forged elements across space like a gardener scattering seeds. Those seeds eventually found their way into the cloud that would become our solar system, and, billions of years later, into us. We are not just living in the Milky Way. We are of the Milky Way. We are its consciousness, a way for the galaxy to know itself. The galaxy made us possible, and in a very real sense, we are its most intricate and wondrous creation. So, after billions of years of assembly, mergers, star formation, and stellar death, what does our completed, or rather, continually evolving galaxy look like today? All right, let's really try to wrap our minds around this. We need to build a model, a mental picture of our galactic home. But to do that, we first have to grapple with a scale that is frankly almost offensive to human intuition. Our brains evolved to understand the distance to a water hole, the height of a tree, the scope of a valley. The scale of a galaxy is so far beyond that, it's almost a different kind of reality. So, let's start with the basic shape. The Milky Way is classified as a barred spiral galaxy. Now, if you've ever seen a picture of the Andromeda Galaxy, which is our closest big galactic neighbor, you have a good idea. Imagine a giant pinwheel, but one where the very center isn't a perfect sphere of light. Instead, it has a bright, elongated bar cutting through it. From the ends of this bar, the majestic spiral arms unwind, curling out into space. That's us. That's what we'd look like from a bird's eye view. But the numbers involved are what truly stagger the mind. The diameter of this cosmic pinwheel, from one edge of its starry disk to the other, is about 100,000 to 120,000 light years. Now we throw that term around, light year, but we have to stop and really feel what it means. It's not a measure of time, it's a measure of distance. It's the distance that a beam of light, traveling at the fastest speed possible in our universe, can cover in a single year. And light is insanely fast. It zips around the Earth's equator about 7.5 times in just 1 second. In the time it takes you to snap your fingers, light could travel to the moon and back. Now hold that thought. Now imagine that incomprehensible speed kept up, not for a second, but for an entire year. The distance it would cover is 9.5 trillion kilometers. That's 9,500,000 kilometers. Or, if you prefer miles, about 6 trillion miles. That's 1 light year. Now multiply that by 100,000. That's the diameter of our galaxy. To travel from one side of the Milky Way to the other, even at the universal speed limit, would take you 100,000 years. Let's make that even more personal. The light from the stars you see at night, those tiny pinpricks of light, has been traveling for years, decades, even centuries to reach your eye. But the faint, misty band of the Milky Way itself is made of stars so distant that their light has been traveling for tens of thousands of years. The photons of light hitting your retina from, say, a star on the far side of the galaxy began their journey around the time when the first Homo sapiens were just beginning to leave Africa and populate the world. You are looking directly into the deep past, seeing those stars not as they are now, but as they were when humanity itself was in its infancy. That's the scale we're dealing with. It's a time machine as much as it is a telescope. Now, this galactic disk isn't a perfectly flat, two-dimensional pancake. It has some thickness to it, a bit of fluff. If the 100,000 light-year diameter is the width of a giant cosmic pizza, then the thickness is like the crust, about 1,000 light-years thick on average. This is the bustling, vibrant heart of the galaxy. This is where most of the action is. This is where you find the vast clouds of gas and dust, the nebulae, that are the nurseries for new stars. This is where you find the brilliant, young, hot blue stars that light up the spiral arms. It's the galactic equivalent of a busy downtown financial district, mixed with industrial zones and brand new housing developments, all buzzing with energy and construction. And where do we live in this vast metropolis? We are not downtown. We are not in the bright, chaotic core. We are out in the suburbs. Our solar system is located in one of the spiral arms, called the Orion Arm or the Local Spur, about 27,000 light-years from the galactic center. This is a pretty good neighborhood. It's relatively quiet. We're far enough from the dense, crowded core to avoid its gravitational dramas and intense radiation. We have a nice, stable orbit around the galactic center, and this brings us to another breathtaking concept, the galactic year. Just as the Earth takes 1 year to orbit the Sun, our Sun, along with the entire solar system, is orbiting the center of the Milky Way. But this orbit is not a quick trip. The Sun is moving at a staggering speed of about 230 kilometers per second, or around 514,000 miles per hour around the galactic center. Even at that mind-melting speed, the journey is so vast that it takes us approximately 220 to 250 million Earth years to complete just one single orbit. This period of time is known as a cosmic year, or a galactic year. Let's sit with that for a second. The last time our solar system was in this exact same position in the Milky Way, the Earth looked very different. The continents were mashed together into the supercontinent Pangaea. The first dinosaurs were just beginning to appear and evolve into the giants that would later dominate the planet. The first mammals were tiny, shrew-like creatures hiding in the shadows. In the entire history of life on Earth, there have only been about 20 galactic years. Complex animal life has existed for perhaps only 3 of those orbits. The entire span of human civilization, from the first cities to today, is less than a blink of an eye, a tiny fraction of a single galactic second. This is the stately, slow, majestic pace of the galactic dance. We are whirling around the center at an incredible speed, yet the scale is so grand that we perceive none of it. Our entire species has existed for less than 1,000th of a single galactic orbit. It's the ultimate reminder that the universe operates on a timescale all its own, a rhythm of billions of years, and we are just fleeting visitors along for the ride. So, let's begin our tour. We're going to start from the very outer limits, the galactic equivalent of the remote, sparsely populated countryside that surrounds a bustling city, and we'll slowly make our way inward. This outermost region is called the galactic halo. Now, if you were to somehow float out here, it would be a very lonely and dark place. This isn't like the bright, sparkling disk of the galaxy we see in pictures. The halo is a vast, mostly empty, spherical cloud that envelops the entire galaxy. It's immense, stretching far beyond the visible edge of the starry disk, but it contains very little of what we traditionally think of as stuff. There's almost no gas and dust out here, and very few stars. If the Milky Way were a chandelier, the disk would be all the bright, glittering crystals, and the halo would be the faint, almost invisible web of wires and framework that holds it all together and gives it its shape. But just because it's mostly empty doesn't mean it's unimportant. In fact, the halo is home to the single biggest, most tantalizing mystery in all of modern science: dark matter. This is a concept that can boggle the mind, so let's take it slow. We've talked a lot about gravity, the force that holds the galaxy together. We can see the visible matter in the galaxy, the hundreds of billions of stars, the glowing gas clouds, the planets. We can add up all that mass and calculate how strong its gravitational pull should be. And then, we can watch how stars on the very outer edges of the galaxy's disk actually move. And here's where things get weird. They are moving way too fast. Imagine a merry-go-round. The horses on the outside have to move much faster than the ones near the center to complete a circle at the same time. That's basic physics. But now, imagine that merry-go-round is spinning so incredibly fast that the horses on the outside are whipping around with such speed that the centrifugal force should easily overcome the weak glue holding them on, and they should be flung off into space. But they aren't. They're staying on, perfectly fine. The only possible explanation is that there is a lot more glue than we can see. There must be some invisible, incredibly strong substance holding them on. That's exactly what's happening in our galaxy. The stars in the outer disk are orbiting the galactic center at velocities that should be impossible, based on the gravitational pull of all the visible matter we can detect. The math clearly says that at those speeds, these stars should have flown off into intergalactic space long ago. The fact that they haven't, the fact that our entire galaxy hasn't simply flown apart, means there must be a huge amount of additional mass that we cannot see. Its gravity is providing the extra glue needed to hold everything together. This invisible mass is what we call dark matter. We call it dark because it doesn't interact with light at all. It doesn't emit it, absorb it, reflect it, or bend it. Well, it does bend it through gravity, but that's a different story. It is completely and utterly transparent. Our telescopes, which are essentially fancy light collectors, are blind to it. We only know it's there because of its gravitational muscle. And it's not just a little bit of it. Based on the motions of stars, we've calculated that this dark matter halo is colossal, containing about 10 times more mass than all the visible stars, gas, and dust in the Milky Way put together. Think about that. Everything you can see in a picture of a galaxy, every single star, every nebula, is just the glittering decoration on top of an immense, invisible mountain of dark matter. This dark matter halo is the true skeleton of our galaxy. It's the framework that formed first after the Big Bang, and the normal visible matter then fell into its gravitational wells to form the stars and galaxies we see. Without dark matter, the Milky Way as we know it would never have formed. It is the ultimate cosmic phantom, and figuring out what it actually is, what tiny, exotic particle could make up this vast, invisible ocean of matter, is one of the greatest scientific quests of our time. But the halo isn't just empty space and mysterious dark matter. It's also a cosmic museum, home to the most ancient relics in the galaxy. Floating out here in the darkness are the oldest stars we know of, over 13 billion years old. These are the survivors from the Milky Way's very infancy, formed from the pristine hydrogen and helium gas that existed before many stars had died and enriched the cosmos. Many of these ancient stars are found in spectacular structures called globular clusters. Imagine a beehive, but instead of bees, it's a dense, spherical swarm of hundreds of thousands of stars, all gravitationally bound together in a ball that might be only 100 light years across. The density of stars in the core of one of these clusters is incredible. If you lived on a planet there, your night sky would be ablaze with thousands of stars as bright as our Venus, creating a perpetual, dazzling twilight. There are about 150 of these globular clusters orbiting our galaxy, like a cloud of distant fireflies, each one a stunning dense island of ancient light. The stars in these clusters are known as population 2 stars. Astronomers classify stars into populations based on their metal content. Now, remember, to an astronomer, a metal is any element heavier than helium. So, population 2 stars are metal poor. They have very low concentrations of elements like carbon, oxygen, and iron. This is because they were born from gas that had been polluted by only the first few generations of supernovae. Their chemical composition is a time capsule, telling us what the universe was like before it was seasoned with the heavier elements. Studying them is like reading a history book from the first chapter of the galaxy. When you look at a globular cluster through a telescope, you are not just looking across space. You are looking back in time, seeing stars that have been shining since before the Milky Way's disk had even fully formed. Besides these clustered ancient stars, the halo is also strewn with isolated old stars and, perhaps most poetically, the ghostly remains of galaxies past. As we learned, the Milky Way grew by consuming smaller dwarf galaxies. When that happens, the victim galaxy is torn apart by our galaxy's gravity, but it doesn't just disappear. Its stars are pulled out into long, looping streams that continue to orbit the galactic center. These are called stellar streams or tidal streams. They are the cosmic equivalent of a faint, ethereal smoke ring, the lingering evidence of a dramatic galactic meal that happened billions of years ago. Astronomers are now mapping dozens of these faint rivers of stars in the halo, each one telling the story of a smaller galaxy that was absorbed into our own, its stars now joining the vast, silent dance in the darkness. So, the halo, though seemingly empty, is actually a place teeming with history, mystery, and the ghosts of galaxies long gone. Moving inward from the halo, we enter the main body of the galaxy, the galactic disk. This is the most iconic part of the Milky Way, the part we see as that river of light in the night sky. The disk is where the galaxy is alive with activity. It's a complex structure, actually composed of a thin disk and a thick disk. The thin disk is where you find the youngest stars, including our Sun, and the vast majority of the galaxy's gas and dust. This is the site of ongoing star formation. The thick disk contains somewhat older stars that orbit a little higher above and below the galactic plane. The disk is not a featureless plane. Its most prominent features are the majestic spiral arms. From our vantage point inside the disk, it's very difficult to map our own galaxy's spiral structure. It's like trying to map the shape of a forest while standing in the middle of it. But through careful observations of the positions and distances of stars and gas clouds, astronomers have pieced together a picture.
The Milky Way is a barred spiral, meaning its center is not a sphere but an elongated bar of stars. From the ends of this bar, the spiral arms unwind. We believe there are 4 major arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm. Our solar system is located in a smaller, partial arm called the Orion Cygnus arm, or simply the local arm, which branches off from the larger Sagittarius arm. You might wonder, are these arms like solid structures, like the fins of a pinwheel? Actually, no. The spiral arms are not permanent structures made of the same stars. They are waves of density, like traffic jams on a cosmic freeway. Imagine a highway where cars are moving along, but there's a construction zone that causes a slowdown. Cars enter the slowdown, they bunch up and move through it more slowly, and then they exit and speed up again. The slowdown itself, the traffic jam, moves along the highway much more slowly than the individual cars. The spiral arms are like that. They are waves of compressed gas and gravity that move through the galactic disk. As clouds of gas and dust enter a spiral arm, the increased density triggers gravitational collapse, leading to a burst of new star formation. This is why the spiral arms appear so bright and prominent. They are lined with brilliant, short-lived, massive blue stars and the glowing pink clouds of gas, nebulae, that are stellar nurseries. These massive stars live for only a few million years and die as supernovae before they can leave the arm. So, the arm is always full of them, making it stand out. Older,
Longer-lived stars, like our Sun, simply pass through the arms on their orbits, spending most of their time in the less dense regions between arms. And it's within these spiral arms, in the vast clouds of gas and dust in the thin disk, that the magic of star birth happens. These clouds are called nebulae, singular nebula, and they are among the most beautiful objects in the universe. A typical nebula is composed of about 70% hydrogen, 28% helium, and that crucial 2% of heavier elements, the dust, which is mostly carbon and silicon compounds. These nebulae are cold, only about 10 to 20 degrees above absolute zero, and they are enormous, often light years across, and containing enough material to form thousands of stars. The process begins when something disturbs the nebula, perhaps the shock wave from a nearby supernova explosion, or the gravitational tug of a passing star, or simply the natural ripples of the density wave in a spiral arm. This disturbance causes a region of the cloud to begin collapsing under its own gravity. As it collapses, it fragments into smaller and smaller clumps. Each clump, a protostar, continues to fall inward, heating up dramatically at its core. When the core temperature hits about 10 million degrees Celsius, a miracle occurs. Nuclear fusion ignites. Hydrogen atoms are fused together to form helium, releasing a tremendous amount of energy in the process. A star is born. The newborn star blows away the remaining gas and dust around it, often revealing itself in a beautiful stellar nursery like the Orion Nebula, which is visible to the naked eye as a fuzzy star in Orion's sword.
But the story doesn't end with the star. The leftover dust and gas that didn't get incorporated into the star often forms a swirling disk around it, called a protoplanetary disk. Within this disk, dust grains collide and stick together, eventually growing into pebbles, then rocks, then planetesimals, and finally, planets. This is how our own solar system formed 4.6 billion years ago. Every star you see in the night sky likely has, or had, planets orbiting it. The galaxy is teeming with worlds. We have now discovered over 5,000 of these exoplanets, and the number grows all the time. They come in a bewildering variety. Hot Jupiters orbiting scorchingly close to their stars, super-Earths, rocky planets larger than our own, ice giants, and even potential Earth-like worlds orbiting in their star's habitable zone, where temperatures might be right for liquid water to exist. The sheer number of stars in the Milky Way, estimated between 100 and 400 billion, suggests an almost unimaginable number of planets. The potential for life out there is a question that drives modern science. Stars live out their lives based on their mass. The most massive stars, as we mentioned, are brilliant, blue, and short-lived. A star 10 times the mass of the Sun might only shine for 20 million years. A star like our Sun, a yellow dwarf, has a much more sedate life, steadily burning its hydrogen for about 10 billion years. And the smallest stars, red dwarfs, are so frugal with their fuel that they can shine for trillions of years, longer than the current age of the universe. But for all stars, the fuel eventually runs out. The death of a star is as important as its birth, for it is in death that stars give back to the galaxy, enriching the interstellar medium with the heavy elements forged in their cores. For a star like the Sun, the end is relatively peaceful. In about 5 billion years, it will exhaust the hydrogen in its core. It will swell into a red giant, swallowing the inner planets, probably including Earth, before gently puffing its outer layers out into space, creating a beautiful glowing shell of gas called a planetary nebula. The hot core left behind will become a white dwarf, a Earth-sized ember
that will slowly cool over billions of years. But for stars more than about 8 times the mass of the Sun, death is spectacularly violent. They end their lives in a cataclysmic explosion known as a supernova. For a brief moment, a single supernova can outshine its entire host galaxy. In the incredible inferno of the explosion, elements are forged through rapid nuclear fusion and neutron capture, creating all the elements heavier than iron on the periodic table, like gold, silver, platinum, and uranium. The explosion blasts these newly created elements, and the star's remains out into space at tremendous speeds, creating an expanding shock wave that can travel for hundreds of light years. This shock wave, in turn, can compress nearby gas clouds, triggering the next round of star formation. It's a magnificent cycle of life, death, and rebirth on a galactic scale. The debris from the supernova, rich in heavy elements, mixes with the interstellar medium, ensuring that the next generation of stars and planets will be made from this enriched material. The very iron in your blood, the calcium in your bones, and the oxygen you breathe were all created in a star that died billions of years ago. We are the universe's way of knowing itself, made from the ashes of long-dead stars. Sometimes the remnant of a supernova is something even more exotic than a cloud of expanding gas. If the core of the exploded star was particularly massive, it can collapse into an unimaginably dense object, a neutron star or a black hole. A neutron star is the city-sized core of a dead star, cramming more than the mass of our sun into a sphere only about 20 kilometers across.
A single sugar cube-sized piece of neutron star material would weigh as much as a mountain. They spin incredibly fast, often dozens of times per second, and if they have a strong magnetic field, they can beam out radiation like a cosmic lighthouse. When these beams sweep across Earth, we detect them as precise pulses of radio waves, and we call these objects pulsars. They are nature's most accurate clocks. Black holes are even more extreme. They are regions of space where gravity is so intense that nothing, not even light, can escape from them. The boundary around them from which nothing can return is called the event horizon. Stellar mass black holes formed from the collapse of massive stars typically weigh between about 5 and 50 solar masses. They are scattered throughout the galaxy. We can't see them directly, but we can detect them by their gravitational influence on companion stars or by the X-rays emitted by the hot gas swirling into them from a nearby star. Now, let's journey to the very heart of the galaxy, the galactic bulge and center. This is the bustling downtown of the Milky Way, a region about 10,000 light-years across, packed tightly with stars. If you were standing on a planet near the galactic center, your night sky would not be dark. It would be ablaze with the light of millions of stars, many times brighter than a full moon on Earth. The stars here are mostly old, population 2 stars, and they orbit the center in every possible direction, creating a swollen, football-shaped central bulge. But the true ruler of this domain lies hidden at the very exact center, a monster lurking in the light, Sagittarius A star. This is the supermassive black hole at the heart of our galaxy. For decades, astronomers suspected its existence based on the frantic orbits of stars near the center, which were whipping around an invisible, incredibly massive object. Then, in 2022, the Event Horizon Telescope collaboration, a global network of radio telescopes, did the impossible. They took a picture of it. Well, not of the black hole itself, but of its shadow, the dark silhouette against the glowing, superheated gas swirling around its event horizon.
Sagittarius A star is immense. It contains about 4.1 million times the mass of our Sun. Yet despite its size, it's currently a relatively quiet and gentle giant. It's not consuming large amounts of material, so it's not shining brightly as an active galactic nucleus or quasar. Some material does fall in, creating a flickering glow, but it's mostly dormant. However, its gravity is the master conductor of the galactic core. The stars that orbit closest to it move at breathtaking speeds. One star, known as S2, comes within just 11 billion miles of the event horizon. That's only about 3 times the distance from the Sun to Neptune. And at its closest approach, it accelerates to a staggering 15 million miles per hour, which is nearly 3% the speed of light. Studying the orbits of these stars is what allowed astronomers to precisely measure the black hole's mass. This region is a natural laboratory for testing Einstein's theory of general relativity under the most extreme gravitational conditions imaginable.
Our galaxy is not alone. It is part of a small gang of galaxies gravitationally bound to each other, known as the local group. The local group is about 10 million light-years across and contains more than 50 galaxies. The 2 biggest members are our Milky Way and the Andromeda Galaxy, M31, which is slightly larger than us. The 3rd largest is the Triangulum Galaxy, M33. The rest are mostly smaller dwarf galaxies that orbit the 2 big spirals like satellites. The most famous of these are the Large and Small Magellanic Clouds, 2 irregular dwarf galaxies easily visible from the southern hemisphere. They are currently orbiting the Milky Way and will likely be absorbed by our galaxy billions of years from now. But the most dramatic future event for our galaxy is on a collision course with us. The Andromeda Galaxy is hurtling towards the Milky Way at about 110 kilometers per second. In about 4.5 billion years, the 2 galaxies will begin a slow gravitational dance that will eventually merge them into a single, giant elliptical galaxy, often nicknamed Milkomeda. It's important to know that a galactic collision is not like 2 cars crashing. Galaxies are mostly empty space. The stars are so far apart that it is extremely unlikely any 2 stars will actually collide. Instead, the galaxies will pass through each other, their gravitational fields dramatically distorting each other's shapes, triggering immense waves of new star formation before settling down into a new blended structure. Our solar system will likely be flung out into a new orbit, but it will probably survive the encounter unscathed. The night sky from Earth, if it still exists then, would be transformed beyond recognition. So after this grand tour of our magnificent, bustling galactic home, it's only natural to wonder, what happens next? What is the ultimate destiny of the Milky Way? It's a story written on a time scale so vast it defies human imagination. A slow-motion ballet that will play out over epochs longer than all of human history to date. It's a future that is, perhaps surprisingly, not one of fire and fury, but of a long, slow, and quiet fading. The dramatic, chaotic youth of our galaxy is largely behind it. The era of major mergers of galactic cannibalism will eventually come to an end. Our impending collision with the Andromeda Galaxy, about 4.5 billion years from now, will be one of the last great acts of violence in our local cosmic neighborhood. After that merger, which will create the new giant galaxy some are calling Milkdromeda or Milkomeda, the universe itself will be working against any further growth. The expansion of the universe, which is actually accelerating due to that other great mystery, dark energy, will eventually push all other galaxies so far away from our own local group that they will fade from view.
receding over a cosmological horizon. Our newly merged galaxy will find itself alone in an ever-darkening void, an island universe in the true sense of the word. But inside our galaxy, life, in a stellar sense, will continue for a long, long time. However, it's a life that is slowly winding down. The primary driver of this decline is fuel. A galaxy is like a vast engine, and its fuel is the cold, neutral gas that floats between the stars, mostly hydrogen. This is the raw material for new stars, but this gas is a finite resource. It gets used up. Some of it gets locked away forever in stars, especially long-lived ones. Some of it gets blown out of the galaxy entirely by powerful supernova explosions. And as the galaxy ages, less and less new gas is accreted from intergalactic space. The rate of star formation, therefore, is not constant. It's like a campfire that's slowly burning through its pile of wood. It peaks early, and then begins a long, slow decline. In about 1 trillion years from now, the last of this usable gas will be exhausted. The last star will be born. It will likely be a small, faint red dwarf, sputtering to life in some forgotten corner of the galaxy. And after that, silence. No new stars will ever form again. The galactic engine will have run out of fuel. From this point on, the story of the Milky Way becomes a story of subtraction, of things ending, of lights going out. The first to go, relatively speaking, are the brilliant, massive stars, but they are already gone. Stars much more massive than our sun live for only a few million years. They are the mayflies of the cosmos, shining with a fierce, blue-white intensity, but dying young in spectacular supernova explosions. They will have vanished from the scene eons before the final star is born. Next are the stars like our own sun. Our sun has a total lifespan of about 10 billion years. It's middle-aged now. In about 5 billion years, it will exhaust the hydrogen fuel in its core, swell into a red giant, likely engulfing the inner planets, and then gently puff its outer layers away into a beautiful planetary nebula, leaving behind its incredibly dense, Earth-sized core, a white dwarf. This white dwarf will initially be searingly hot, an ember of what once was, but with no internal fusion to keep it warm. It will slowly, inexorably cool down over billions of years. Every star like our sun will follow this path. They will die not with a bang, but with a whisper, leaving behind these fading white dwarf remnants. So, who is left in this trillion-year-old future? The galaxy's population will be dominated by two groups. The first is the long-lived red dwarfs. These are the smallest and coolest kind of star. They are incredibly frugal with their nuclear fuel, burning it so slowly that their lifespans are measured in trillions of years. A red dwarf born near the beginning of the galaxy is still in its infancy today. In the far future, these dim, red stars will be the sole sources of light and warmth in the galaxy. They will be the last living stars. The second group is the dead. The galaxy will be filled with the cooling embers of past stellar generations. The white dwarfs, the cores of sun-like stars, the neutron stars, the ultra-dense cores left from supernovae, and black holes, both stellar mass and the supermassive one at the center. This will be the galaxy's population, a handful of faint red living stars amidst a vast sea of dark, dead stellar corpses. The character of the galaxy will change completely. It will grow darker and redder. The brilliant blue-white light of young star clusters and the glowing pink of stellar nurseries will be gone forever. The only light will be the faint, ruddy glow of the countless red dwarfs. It will be a somber, quiet place. But even the red dwarfs are not immortal. Their incredible longevity is still finite. In about 1 trillion years from now, the last of this usable gas will be exhausted. The last star will be born. It will likely be a small, faint red dwarf, sputtering to life in some forgotten corner of the galaxy. And after that, silence. No new stars will ever form again. The galactic engine will have run out of fuel. From this point on, the story of the Milky Way becomes a story of subtraction, of things ending, of lights going out. The first to go, relatively speaking, are the brilliant, massive stars, but they are already gone. Stars much more massive than our sun live for only a few million years. They are the mayflies of the cosmos, shining with a fierce, blue-white intensity, but dying young in spectacular supernova explosions. They will have vanished from the scene eons before the final star is born. Next are the stars like our own sun. Our sun has a total lifespan of about 10 billion years. It's middle-aged now. In about 5 billion years, it will exhaust the hydrogen fuel in its core, swell into a red giant, likely engulfing the inner planets, and then gently puff its outer layers away into a beautiful planetary nebula, leaving behind its incredibly dense, Earth-sized core, a white dwarf. This white dwarf will initially be searingly hot, an ember of what once was, but with no internal fusion to keep it warm, it will slowly, inexorably cool down over billions of years. Every star like our sun will follow this path. They will die not with a bang, but with a whisper, leaving behind these fading white dwarf remnants. So, who is left in this trillion-year-old future? The galaxy's population will be dominated by two groups. The first is the long-lived red dwarfs. These are the smallest and coolest kind of star. They are incredibly frugal with their nuclear fuel, burning it so slowly that their lifespans are measured in trillions of years. A red dwarf born near the beginning of the galaxy is still in its infancy today. In the far future, these dim red stars will be the sole sources of light and warmth in the galaxy. They will be the last living stars. The second group is the dead. The galaxy will be filled with the cooling embers of past stellar generations. The white dwarfs, the cores of sun-like stars, the neutron stars, the ultra-dense cores left from supernovae, and black holes, both stellar mass and the supermassive one at the center. This will be the galaxy's population, a handful of faint, red, living stars amidst a vast sea of dark, dead stellar corpses. The character of the galaxy will change completely. It will grow darker and redder. The brilliant blue-white light of young star clusters and the glowing pink of stellar nurseries will be gone forever. The only light will be the faint, ruddy glow of the countless red dwarfs. It will be a somber, quiet place. But even the red dwarfs are not immortal. Their incredible longevity is still finite, on timescales so long that they have no meaning to our human experience. Tens of trillions, even hundreds of trillions of years. The last red dwarf will finally, reluctantly, use up the last of its hydrogen fuel. It will not go out with a dramatic explosion. It will simply fade, cooling into a dark, inert ball of gas known as a black dwarf. It will join the other remnants. And what of the white dwarfs? They will have continued to cool during all this time. A white dwarf starts white hot, but over many billions of years, it will cool to yellow, then red, and eventually it will emit no visible light at all. It will become a black dwarf, a cold, dark sphere of crystallized carbon and oxygen, perhaps resembling a giant, planet-sized diamond, drifting in the absolute zero cold of space. The process of a white dwarf cooling to a black dwarf takes so long that it's believed the current age of the universe, 13.8 billion years, is not even long enough for the first white dwarfs to have reached this state. The first black dwarf in the universe has not yet been born. So, the galaxy's final state will be a dark graveyard, a vast collection of black dwarfs, neutron stars, and black holes, all silently, eternally orbiting the galactic center. There will be no light, no heat, no new energy. It will be a frozen, mechanical clockwork of orbits in the profound dark. And what of the great anchor at the center? The supermassive black hole Sagittarius A. Even its reign is not forever. Thanks to a strange quantum mechanical process predicted by Stephen Hawking, black holes are not entirely black. They can slowly lose mass by emitting a faint trickle of particles now known as Hawking radiation. For a massive black hole, this process is incredibly slow. A black hole with the mass of our sun would take longer than the current age of the universe to evaporate. For a supermassive black hole millions of times heavier, the time scale is almost unimaginably long, on the order of 10-100 years, A1 followed by 100 zeros, a number so large it has its own name, a Google. But given enough time, even this monstrous beast will, in a final burst of energy, evaporate completely away. This is the far, far future as we currently understand it, a quiet, dark, and cold end. But it's important to remember that this is not an ending in the sense of a tragedy. It's a natural conclusion to the life cycle of a galaxy. The Milky Way had a vibrant, brilliant, and creative life. It forged the elements and built the worlds that allowed for us to exist and to look up at the night sky and wonder. Its story, from a tiny ripple in the early universe to a glittering spiral to a dark relic, is one of the most epic narratives it is possible to conceive. And in a way, the fact that we can understand and tell this story is a beautiful and profound counterpoint to that distant darkness. We are the universe's consciousness, and for a brief shining moment, we are here to bear witness to its majesty. But for now, for us, the Milky Way is a vibrant, dynamic, and beautiful home. It is a cosmic engine that has taken the primordial hydrogen from the Big Bang and processed it through generations of stars, creating the diversity of elements that allowed for planets, oceans, and life. Every time you look up at that faint milky band in the night sky, remember what you are truly seeing. You are seeing the collective light of countless suns. You are seeing the stellar nurseries where new solar systems are being built. You are seeing the radiance of stars that died long ago, whose remains now reside in you. You are looking at the vast spiral disk in which we have our being, the invisible halo of dark matter that holds it all together, and the distant, mysterious center, where a silent giant holds sway. It is our city of stars, and we are, for a fleeting moment, conscious citizens within it. We are part of this grand story, a story that began over 13 billion years ago, and will continue for trillions more. And that connection, that sense of belonging to something so vast and beautiful, is perhaps the greatest gift that exploring our Milky Way galaxy gives to us. Good night. Have a deep sleep.
Hello, my dear dreamers, and welcome back to Hayfi Sleep, where we calm the mind and expand the universe one star at a time. Whether you're tuning in to unwind after a long day, to drift off into a peaceful slumber, or simply to get lost in a story bigger than ourselves, I am so incredibly glad you're here. Tonight, we're going on our grandest adventure yet. We're leaving all our everyday worries behind and stepping out our front door, not just onto the porch, but into the cosmos itself. We're going to answer a seemingly simple question that has a truly breathtaking answer. How big, actually, is our home, the Milky Way Galaxy? We're going to shrink the universe down to a scale we can understand, and in doing so, I promise you will see the night sky and your place in it in a completely new light. This is a story I'm so excited to share with you. If you're enjoying our journey together, please do consider subscribing to Happy Sleep. It truly helps this channel grow and allows me to bring more peaceful explorations to you. And if you're feeling it, give this video a like. It lets me know what kind of stories you love. I'd also love to hear from you in the comments below. Where in the world are you listening from tonight, and what time is it for you? Are you cozying down for the night, or is this your morning moment of calm? It's always wonderful to feel our little community of stargazers stretching across the globe. So now, find your most comfortable position, take a gentle, deep breath, and let your imagination float free. Let's begin our journey to understand the magnificent scale of our galactic home. You know, sometimes on a really clear, dark night, far away from the glow of the city lights, you look up and you see it. That faint, hazy band of light stretching across the sky like a river of spilt milk. The Milky Way. It's been a constant, silent companion to humanity for all of our existence, a source of stories, myths, and wonder. We point to it, we name our galaxy after it, and we feel a sense of connection to it. But I have to ask you a question, a really simple one, and honestly, the answer is going to blow your mind. How big actually is it? I mean, we hear the words, the Milky Way Galaxy. It sounds grand, doesn't it? Immense. But what does that mean? Is it as big as, say, the distance from the Earth to the Moon? Is it bigger than our entire solar system? The words we use can become so familiar that they lose their meaning, like saying a billion years. It just rolls off the tongue. But the reality of it is almost impossible for our brains to truly grasp. So, let's try. Let's take a journey, not on a spaceship, but with our imaginations and really truly try to understand the scale of our cosmic home. And I promise you, by the end of this, you will never look at that hazy band of light in the same way again. First, we need a starting point. Let's start with something we know. You, sitting there, listening to this, or me, standing here talking. We are about, on average, let's say 1.7 meters tall, roughly. That's our scale. Our world, the Earth, is about 12,742 kilometers in diameter. Now that number, 12,742 kilometers, is already too big to really feel. So let's shrink it down. Imagine a beautiful, polished marble about 1 centimeter across, a lovely blue and white swirl. That's Earth. This little marble is our entire world, everything we've ever known, every person, every ocean, every mountain range, all contained on the surface of this 1 centimeter sphere. It's humbling, isn't it? So, let's just pause for a moment on that thought, shall we? This 1 centimeter marble, this entire world. It's a powerful image, but how did we even arrive at it? How do we know with such precision that our home is 12,742 kilometers across? It's not like we can wrap a giant tape measure around the equator, right? Well, the story of how we learned the size of our own planet is a testament to human curiosity and cleverness, and it started a very, very long time ago. Imagine this. Over 2,000 years ago, in ancient Egypt, a man named Eratosthenes. He was the chief librarian at the famous Library of Alexandria, a place teeming with all the knowledge of the ancient world. He heard about a curious phenomenon in a town called Syene, to the south. There, on the summer solstice, at noon, the sun would be directly overhead. So perfectly overhead that it would shine straight down the deepest wells, lighting up the water at the bottom, and vertical pillars would cast no shadow at all. Nothing. The sun was just right there. Now Eratosthenes, being a brilliantly inquisitive mind, decided to check if the same thing happened in Alexandria. So, on the very same day, at the very same time, he went out and measured the shadow cast by a tall vertical obelisk, and he found a shadow. It wasn't a long, dramatic shadow, but it was there. A definite, measurable angle. This told him one thing for certain. The Earth's surface was curved. If it were flat, both places would have the same shadow, or no shadow at all. But they didn't. Using some elegant geometry, he calculated that the angle of the shadow in Alexandria was about 7.2 degrees. Now, a full circle is 360 degrees, and 7.2 is exactly 1/50th of 360. This meant that the distance between Alexandria and Sienne had to be 1/50th of the Earth's total circumference. It was a breathtaking leap of logic. He then hired a bimatist, a professional distance walker, to pace out the exact distance between the two cities. The measurement came out to about 5,000 stadia. Now, a stadium was an ancient unit of length, and while we're not exactly sure of its modern equivalent, if we use the most commonly accepted conversion, Eratosthenes calculated a circumference for the Earth that was within a stunning 1% of the value we know today, about 40,000 kilometers. And since the diameter is simply the circumference divided by pi, that famous number 3.11415, he had in 200 BC effectively determined the Earth was about 12,600 kilometers across. Isn't that incredible? With little more than a stick, a shadow, and a brilliantly logical mind, a man figured out the size of our entire world. Today, with our orbiting satellites and powerful lasers, we've refined that number. We now know the Earth isn't a perfect sphere. All that spinning one full turn every single day causes it to bulge out slightly at the middle, like a person spinning pizza dough. So, the diameter from pole to pole, the polar diameter, is a bit smaller, about 12,714 kilometers. The diameter across the equator, the equatorial diameter, is a bit larger, about 12,756 kilometers. When we say about 12,742 kilometers, we're taking the mean diameter, the lovely, perfect average of those two numbers. So our 1 centimeter marble is a beautifully simplified version of this slightly squashed, beautifully imperfect spheroid we call home. Now let's come back to you, the listener. I started by saying we are, on average, about 1.7 meters tall. That's roughly 5 feet and 7 inches. Where does that number come from? It's a global average for adult men, a kind of cosmic common denominator for humanity. It's fascinating to think that this average isn't static. It changes from country to country and even across time. For instance, due to better nutrition and healthcare, the average height of people in many parts of the world has been steadily increasing over the past century. In some northern European countries, the average for men is now well over 1.8 meters. But 1.7 meters gives us a wonderful, relatable baseline, a personal ruler against which we can measure everything else. And this is where the real magic of our scaling exercise begins. We have our personal ruler, you, at 1.7 meters, and we have our planet's diameter, 12,642,000 meters. To create our model, we are going to shrink everything down proportionally. We are going to divide the Earth's true size by its own diameter to get it down to that 1 centimeter marble. It's a ratio of 1 to 1.274 billion. Every single thing in our model, every distance, every size, will be scaled down by that same mind-numbing factor. So, if you are 1.7 meters tall in reality in our model world, you would be shrunk down to a microscopic 1.33 billionths of a meter tall. That's far, far smaller than a dust mite, utterly invisible to the naked eye. This immediately gives you a sense of just how vast the Earth is compared to us. Our entire physical being is completely insignificant on the scale of the planet itself. But we are imagining this, so you get to keep your perspective. You are a gentle giant leaning over to look at this beautiful swirling marble that contains all of human civilization. Now let's place this marble in its cosmic context, its neighborhood, which is our solar system. Our sun, as we said, is phenomenally big. Its actual diameter is about 1,392,000 kilometers. To figure out how big it is in our model, we take that enormous number and divide it by our scaling factor of 1.274 billion. Do the math, and it comes out to about 109 centimeters. That's 1.09 meters, a sphere that stands just a little taller than the waist of an average adult. Picture a ball as tall as a kitchen countertop or the seat of a bar stool. That's our sun. Now compare that to our 1 centimeter Earth marble. The sun isn't just a little bigger, it is a colossal dominating presence. In fact, you could fit well over 1 million Earths inside the actual sun. The sheer volume is almost incomprehensible, and the distance between them is even more so. The actual average distance from the Earth to the Sun is about 150 million kilometers, a unit we call 1 astronomical unit, or 1 AU. Scaling this down by our factor gives us 150,000 divided by 1,274,000, which is approximately 0.11177 kilometers. Now let's convert that to meters, which is 117.7 meters. That's the length of an American football field, including the end zones, or a full-sized international soccer pitch. So picture this. You are standing next to a beautiful, warm, glowing sphere that's about the height of a person. You hold up a tiny 1-centimeter marble, and then you have to walk the entire length of a soccer field to place that marble in its orbit. All that empty space, just for one single tiny planet. The Sun is a person-sized sphere, and our world is a marble over 100 meters away. The emptiness is already starting to feel profound. But wait, we are just getting started. Our solar system is so much more than just the Sun and the Earth. Let's take a quick tour of the rest of the planetary family in our scaled-down model. Let's start with the inner rocky planets. Mercury, the innermost planet, is a tiny speck, only about 0.38 centimeters in our model, smaller than a peppercorn. It would orbit very close to our person-sized Sun, maybe just 45 meters away. Venus, often called Earth's twin, is a little larger, about 0.95 centimeters. Almost a 1-centimeter marble like Earth, but a bit smaller and sweltering. It orbits about 86 meters from the Sun. Then there's our marble, Earth, at 117 meters. Just a bit further out, at around 178 meters, is Mars, the red planet. In our model, it's a small p, about 0.53 centimeters across. This is the next stop for human exploration, a world that captivates our imagination, and in our model, it's just a reddish pea about half a soccer field further out from Earth. Now, prepare for the giants. The asteroid belt is a scattered collection of dust and rocks between Mars and the next planet. And then, we meet Jupiter. Jupiter is the king of the planets. Its actual diameter is about 139,822 kilometers. In our model, that translates to a sphere about 11 centimeters across. Picture a large grapefruit, a big, striped, beautiful grapefruit. But where is it? It orbits the Sun from a staggering distance. Its actual average distance from the Sun is about 5.2 AU. In our model, that's over 600 meters away from our person-sized Sun. You'd have to walk the length of 6 soccer fields to get from the Sun to Jupiter. A grapefruit, 6 football fields away from a person-sized sphere. It keeps going. Saturn, with its magnificent wide rings that would stretch out even further in our model, is about a 9-centimeter orange, and it's a full kilometer away from the Sun. Uranus and Neptune, the icy giants, are even more remote. Uranus, a small billiard ball about 4 centimeters across, is over 2 kilometers away, and Neptune, a similar-sized billiard ball, is an almost unbelievable 3.5 kilometers from our central Sun. Just let that sink in. In our model where the Earth is a marble you can hold between your finger and thumb, you'd need to get in your car and drive a few miles to reach the orbit of Neptune. But here's the truly humbling part. Our solar system doesn't even end with Neptune. Out beyond the last official planet lies the Kuiper Belt, a disc-shaped region of icy bodies, home to dwarf planets like Pluto. It extends out to about 50 AU from the Sun. On our scale, that's almost 6 kilometers away. And even that isn't the true edge. Enveloping our entire solar system is the theoretical Oort cloud, a vast spherical shell of icy objects that marks the very furthest reach of the Sun's gravitational influence. It's thought to extend out to a mind-boggling 100,000 AU. On our 1-centimeter Earth scale, the outer edge of the Oort cloud would be about 10,000 kilometers away. That's the actual distance from New York City to Sydney, Australia. All of that immensity, all of that breathtaking empty distance from a person-sized Sun in the center to a 10,000-kilometer distant shell of ice is just our one single solitary solar system. It's the house, the neighborhood, the entire city block in which our little Earth marble lives. And as we will soon see, this entire vast construct is just one tiny speck in an even grander structure. Now, take a deep breath, because we're about to take a step out that front door. The sun is not alone. It's one star among, well, we need a new number. A really, really big number. The Milky Way Galaxy, our home galaxy, is a collection of stars, gas, dust, and dark matter all bound together by gravity. And the number of stars in it is staggering. The best estimates from astronomers suggest there are between 100 billion and 400 billion stars in the Milky Way. Let's take the lower, more conservative estimate just to be safe, 100 billion stars. So let's talk about this new number, 100 billion stars. You might be wondering how on Earth, or rather how outside of Earth, do astronomers even arrive at such a figure? It's not like they can count every single star one by one like taking a cosmic census. The method is much more clever, and it starts with weighing our galaxy. Just like you might estimate the number of apples in a bag by knowing its total weight and the average weight of one apple, astronomers first determine the total mass of the Milky Way. They do this by watching how the galaxy spins. Everything in the Milky Way, including our sun, is orbiting the galactic center, held in place by the immense force of gravity. By measuring the speeds of stars at different distances from the center, they can calculate how much mass must be there to keep them from flying off into the void. This is where things get really strange, because the mass they calculate is far, far greater than the mass we can see from all the stars, gas, and dust put together. In fact, only about 10% of the galaxy's mass is the stuff we can see. The rest, the overwhelming majority, is something mysterious and invisible called dark matter. It's the hidden scaffolding of our galaxy, and its gravitational pull is the true engine of its rotation. So, once astronomers subtract the estimated mass of this dark matter, they're left with the mass of all the visible stuff. From there, they can estimate how much of that visible mass is locked up in stars, and by assuming an average mass for a typical star, they arrive at that staggering number, 100 to 400 billion suns. It's an estimate, a best guess based on incredible science, and it reminds us that there is still so much about our own home that we are working to understand. Now, let's come back to that beach. You have your 100 billion grains of sand, each one a star. But our sun, our particular grain, isn't just floating in a random, formless cloud. No, it's part of an immense, organized structure, a city of stars with a specific shape and geography. You described it perfectly, a barred spiral galaxy. Let's paint a more detailed picture of this city. Imagine that central bar not as a solid rod, but as a brilliant, elongated hub of stars, a cosmic downtown that is constantly abuzz with activity. This central bulge is thick with stars, many of them ancient and glowing with a reddish or yellowish light. If you could stand on a planet inside this bulge, your night sky wouldn't be black. It would be a perpetual blazing twilight, with millions of stars brighter than Venus is in our sky, all crammed together. It's a crowded, magnificent metropolis, and flowing out from the ends of this central bar are the great spiral arms. Think of them not as rigid, solid structures, but as cosmic traffic jams, or like waves of compression moving through the galaxy. Imagine a busy highway where a slowdown causes cars to bunch up. The cars themselves are always moving in and out of the jam, but the bunch-up itself persists and moves along the road. In our galaxy, the cars are the stars, gas, and dust. As they orbit the galactic center, they enter these spiral arms, these regions of higher density. Here, the gas and dust are squeezed together, and this compression is the primary trigger for the birth of new, brilliant, hot stars. This is why the spiral arms look so bright and dramatic in pictures of other galaxies. They are the stellar nurseries, the vibrant, glowing districts where the next generation of stars is lighting up. The major arms, with names like Scutum Centaurus and Perseus, are the grandest boulevards, packed with both young and old stars. Between them are the minor arms, like Norma and Sagittarius, which are a bit quieter, filled more with gas and pockets of star-forming activity. And this brings us to our own, very specific address in this colossal city. Our solar system, that one grain of sand we've been following, is not in the bright, bustling downtown bulge. It's not even on one of the major glittering spiral arm boulevards. We are, as you said, out in the suburbs, on a quieter partial arm called the Orion Arm, or Orion Spur. We are nestled between the much larger Sagittarius and Perseus arms. Our exact address is about 25,000 to 28,000 light-years from the galactic center. From our quiet suburban porch in the Orion Spur, we have a pretty good, albeit edge-on view of the rest of the city. When we look up at that hazy, milky band in the night sky, we are looking along the plane of the galactic disk, through the crowded streets of our own spiral arm and beyond, toward the even more densely packed stars of the inner galaxy and the brilliant downtown bulge. The dark patches we see within that Milky River are not empty space. They are vast, dark clouds of cosmic dust, blocking the light from the billions of stars behind them, creating what look like cosmic alleyways and tunnels. So, to summarize our cosmic location, we live on a 1-centimeter marble, orbiting a person-sized sun, which is one of roughly 100 billion other stars, all arranged in a vast spinning pinwheel that is 100,000 light-years across. Our little solar system is situated in a quiet suburban arm, roughly halfway from the vibrant center, slowly orbiting the heart of the galaxy at a breathtaking 828,000 kilometers per hour. And even at that incredible speed, it still takes us a long, long time to complete just one trip around, about 230 million years. The last time our sun was in this particular spot in its galactic orbit, the dinosaurs were just beginning their reign on Earth. It's a perspective that is at once both humbling and exhilarating. We are tiny, we are remote, and we are temporary on this cosmic timescale. And yet we are part of it. We have managed to figure out our place in this immense city of suns. We have mapped the spiral arms from within, weighed the galaxy, and counted its stellar citizens. That tiny, conscious grain of life on that 1-centimeter marble has looked up and understood the architecture of its home, a home of breathtaking scale and beauty. And this brings us to the physical dimensions, the actual mileage of this thing. How wide is the Milky Way? If you could somehow get a cosmic tape measure and stretch it from one edge of the galactic disk to the other, what would it read? The answer is about 100,000 light-years. There's that term, light-year. It's crucial we understand this because it's the only unit that makes any sense at this scale. A light-year is not a measure of time. It's a measure of distance. It's the distance that a beam of light, traveling at the absolute speed limit of the universe, covers in one single year. So, let's linger on this concept of the light year for a moment because it's the foundation of everything that follows. Light moves at a speed that is, for all intents and purposes, the ultimate speed limit of the universe. It's 300,000 kilometers per second. To put a little more perspective on that, if you could ride a beam of light, you could travel from the Earth to the Moon in just over 1 second. Think about that. The Apollo astronauts took about 3 days to make that journey. Light does it in the time it takes you to snap your fingers. Now, stretch that out. Not for a second, not for a minute, not for a day, but for an entire year. A single year has 31,536,000 seconds. So, the distance light covers in 1 year is that staggering speed multiplied by that staggering number of seconds. The math gives us approximately 9.46 trillion kilometers. That's 1 light year. A trillion, just to remind ourselves, is a 1 followed by 12 zeros. So 946 trillion is 9,460,000 kilometers. It's a number so vast that it loses all connection to the world we know. We can't picture a trillion of anything, let alone a trillion kilometers. Now, take a deep breath and hold that immensity in your mind, because the Milky Way Galaxy, our island universe, is about 100,000 light-years in diameter. That means it would take a beam of light traveling at the universe's ultimate speed, 100,000 years to go from one edge of our galaxy to the other. Let's just sit with that for a second. Every single thing we see in the night sky, every star, every nebula is a part of this structure. The light from those stars has been traveling for years, decades, centuries, even millennia, just to reach our eyes. When we look at the far-off regions of our own galaxy, we are looking back in time, seeing them not as they are now, but as they were thousands of years ago. Now, if we do the multiplication, the diameter of the Milky Way in kilometers becomes a number that is almost comically large, 100,000 multiplied by 9.46 trillion. That's 946,000 kilometers, a 9.46 with 17 zeros after it. This number has no analog in human experience. It's useless for anything other than giving us a sense of profound awe and a slight headache. Our brains simply are not wired to process this. We evolved to understand the distance to a water hole, the height of a tree, the walk to the next village. We have no innate sense for a quintillion of anything. So to have any hope of understanding, we must go back to our scale model. We must shrink the universe down to a size we can walk across. Let's return to our beautiful 1 centimeter marble that is our Earth. On this scale, as we established, our Sun is a person-sized sphere about 117 meters away. Now we need to figure out how big a light year is on this same scale. If our 1 centimeter marble represents 12,742 kilometers, then 1 centimeter in our model represents 1.274 billion centimeters in reality. This is our scaling factor. A light year is 9.46 trillion kilometers, which is 9.46 x 10^12 kilometers. To find its model size, we divide that by our scaling factor of 1.274 x 10^9 kilometer per model centimeter. The math works out to roughly 7,400 centimeters for 1 light year in our model. Now 7,400 centimeters is 74 meters. So on our model, where Earth is a marble, a single light year is represented by a distance of about 74 meters. That's roughly the length of an Olympic-sized swimming pool, or a little longer than an American football field. Now for the grand finale. The Milky Way is 100,000 light years across. So we multiply our 74-meter light year by 100,000. That gives us 7,400,000 meters, which is 7,400 kilometers. What is 7,400 kilometers across? The contiguous United States from the Pacific coast of California to the Atlantic coast of Maine is almost exactly that distance. It's a near-perfect fit. So let's make this real. Picture a map of the United States. You are standing on a beach in Los Angeles, California. That point on the map represents one edge of the Milky Way Galaxy. Now you get in a car and you start driving. You drive through the deserts of Arizona, the plains of Texas, the rolling hills of the Midwest, the cities of the East Coast, and finally, after a journey of thousands of miles, you arrive in New York City. That point on the map represents the opposite edge of the galaxy. The entire, vast continental United States is now the stage for our model of the Milky Way. Now, let's populate this continental scale model. Remember our 100 billion stars? In this model, each and every star, each sun, each potential solar system, is represented by a single fine grain of sand. Our own sun, which in our solar system model was a person-sized sphere, has now been shrunk down to one of those tiny, almost microscopic specks. And these grains of sand are not piled up in a desert. They are scattered, with immense amounts of empty space between them across the entire breadth of the United States. And where is our particular grain of sand, our solar system, located? Well, we know that our sun is not at the center of the galaxy. We're out in the suburbs in a spiral arm known as the Orion Arm or Orion Spur, about 26,000 to 28,000 light years from the galactic center. On our USA map, if the total width is 100,000 light years, then halfway would be 50,000 light years. We're a bit closer in than that. If the galactic center is, say, somewhere in the vicinity of Kansas City, then our position, about 2/3 of the way from the center to the edge, would place our solar system, our single grain of sand, somewhere in the vicinity of Omaha, Nebraska. So, from our vantage point on our tiny speck in Omaha, we are trying to comprehend the structure of an entire continent. This model does more than just help us with the width. It also gives us a feeling for the galaxy's thickness. The Milky Way is a flat disk, but it's not two-dimensional. It has thickness. At the spiral arms where we are, the disk is about 1,000 light years thick. On our USA model, where the width is 7,400 kilometers, 1,000 light years scale down to about 74 kilometers. So the thickness of the galactic disk where we live is like the height of a commercial airliner's cruising altitude above the surface of our map. Our entire sprawling continental scale galaxy is, for the most part, only about as thick as a short flight is high. It's an incredibly flat pancake. This is precisely why we see the Milky Way as a band in our night sky. We are inside the pancake, looking through its long, star-filled plane. When we look away from the band, we are looking out through the thin edge of the disk into the much emptier intergalactic space. But there's more. At the very center of the galaxy, there is a bulge. This central bulge is much thicker, about 10,000 light-years across or more. On our scale, that's a region about 740 kilometers thick, a much fatter, more rounded hub at the center of our cosmic pancake. And right at the heart of that bulge, at the center of our entire continent-sized model, sits the supermassive black hole, Sagittarius A star. On our scale, this object, which has a mass of millions of suns, would be smaller than a single atom. Its gravitational influence, however, is what helps shape the entire central bulge and anchors the grand rotation of the galaxy. It's the silent, invisible monarch sitting on the throne at the center of everything. So, when we ask, how wide is the Milky Way? The answer is not just a number. It is an experience. It is the feeling of looking at a map of a whole country and understanding that you live on a speck of dust somewhere in the middle of it, a speck that is orbiting another invisible speck at the center. It is the realization that the hazy river of light you see on a clear night is the combined glow of countless other dust specks, stretching all the way from your horizon in Los Angeles to the opposite horizon in New York. The scale is inhuman, but by building these models, by telling these stories, we can, for a moment, almost grasp it. And in that moment, we achieve something wonderful. We make the universe feel a little bit more like home. Let that sink in for a moment. The entirety of human history, every triumph and tragedy, every work of art, every whispered secret, every life that has ever been lived, has all occurred on the surface of a 1-centimeter marble, which is orbiting a single grain of sand, which is located somewhere near Omaha, in a structure that spans the entire width of the United States of America. The sheer, raw, staggering emptiness of space becomes apparent. The distance from our grain of sand to the next nearest one, which is the Alpha Centauri system, on this scale, is about 4.5 kilometers. That's how far you'd have to walk to find the next grain of sand in this vast continental emptiness. It's no wonder space travel between stars is so fantastically difficult. We are isolated in the most profound sense of the word. But we've only talked about the width. What about the thickness? The galaxy isn't a flat disk like a DVD. It's more like a fried egg with a bulging center and a thinner disk. The central bulge, where the long bar of stars resides, is the yolk of the egg. This region is about 10,000 to 12,000 light-years thick. That's still 1,000 light-years of packed stars. The disk itself, where we live out in the suburbs, is much thinner. It's about 1,000 light-years thick on average. So, on our USA scale, if the width is from coast to coast, the thickness of the disk where we are is only about the height of a 10-story building. We are living in an incredibly flat, pancake-like structure on a continental scale. This is why when we look up at the night sky, we see the Milky Way as a band. We are inside the pancake looking through its long, star-filled plane. When we look away from the band, we are looking out of the thin edge of the disk into the much emptier intergalactic space, and thus we see far fewer stars. Now, let's take a trip, an imaginary journey from one edge of the galaxy to the other. We'll hop aboard a magical ship that can travel at the speed of light. We push the throttle forward and the universe blurs around us. We are moving at 300,000 kilometers per second. Let's see what we'd encounter. Now, traveling at the speed of light isn't like traveling in a car or a plane, where you feel the wind rushing past. At this speed, the universe itself undergoes a strange transformation due to the effects of relativity. But for our journey, let's imagine we can simply observe everything as it is, frozen in a single eternal moment of our passage. The universe blurs not because things are moving past us fast, but because we are moving through space itself, a silent, ghostly vessel on the ultimate express train. We begin our journey at the very outer fringe in the galactic halo. Imagine this as the galaxy's remote, sprawling countryside. It's not a place you'd find on most tourist maps of the Milky Way. It's a vast, and I mean vast spherical region that envelops the entire disk of the galaxy like a faint cosmic fog. If the disk of the galaxy is the vibrant lit-up city, the halo is the dark, mostly empty countryside for thousands of miles in every direction, including above and below. It's not completely empty, but it's incredibly sparse. The stars here are few and far between, and they are special. They are the ancient relics, the grandparents of the galaxy. These are population 2 stars, and they are composed almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang. They contain very few of the heavier elements, the carbon, oxygen, iron that make up our world and our bodies, because those elements hadn't been cooked up in stellar furnaces yet when these stars were born. They are living fossils telling the story of the Milky Way's violent, chaotic infancy, a time when the galaxy was first pulling itself together from collapsing clouds of gas and through violent mergers with smaller dwarf galaxies. As we gaze out from our ship into this profound darkness, we might see them, these ancient suns, glowing with a steady, often reddish light. They are old and stable, burning slowly, but the real jewels of the halo are the globular clusters. The text mentioned over 150 of them, and each one is a breathtaking sight. Picture a beehive, but a beehive made not of bees, but of stars. A single globular cluster is a dense, spherical swarm of hundreds of thousands, sometimes even millions, of stars, all gravitationally bound together in a space that might only be a few hundred light years across. To put that in perspective, if our solar system were placed at the center of a globular cluster, our night sky would be filled with tens of thousands of stars as bright as the planet Venus, creating a perpetual dazzling twilight that would outshine the moon. From our ship, as we pass one at a distance, it doesn't look like a collection of individual points of light. It looks like a fuzzy, glowing ball, a celestial dandelion puff made of ancient starlight. These clusters are orbiting the galactic center on long, looping paths that take them far out into the halo and then back in, like bees dutifully, endlessly circling their hive. And then there's the halo's most mysterious and dominant resident, dark matter. We can't see it. Our ship's sensors can't detect it directly. It doesn't emit, absorb, or reflect any light. It is completely and utterly invisible. So how do we know it's here? We can feel it. Well, not us, but the galaxy feels it. The entire galaxy is spinning, and the stars in the outer disk are orbiting far too quickly to be held in place by the gravity of all the visible matter we can see. All the stars, gas, and dust. It's as if you saw a child on a merry-go-round spinning at an incredible speed. But when you looked, there was no merry-go-round, just the child, magically whirling around in a circle. The only explanation is that there is something else there, something we can't see, providing the extra gravitational pull. That something is the dark matter halo. It makes up the vast majority of the galaxy's mass, perhaps as much as 90% of it. It is the invisible skeleton, the gravitational glue, upon which the visible galaxy is built. As we cruise through the halo, we are sailing through an ocean of this mysterious substance, a silent, unseen ocean whose waves and currents dictate the motion of everything we can see. After what feels like an eternity in the quiet darkness of the halo, we begin our descent into the galactic disk. The change is gradual at first. The number of stars per cubic light year slowly begins to increase. It's like flying over a dark rural landscape at night and seeing the occasional isolated farmhouse light begin to give way to the dim glow of a distant suburb. We are now entering the thin, flat plane of the galaxy. This is the Milky Way's main stellar city, and we are first arriving in our own neighborhood, the Orion Arm. The character of space changes here. It's no longer the pristine, empty void of the halo. Now we are moving through the interstellar medium, or ISM. Think of it as the galaxy's atmosphere. It's a fantastically thin soup of gas, about 99% hydrogen and helium, and microscopic dust grains. When I say thin, I mean it's a better vacuum than any we can create in our best laboratories on Earth. But spread across light years, this thin soup adds up, and it's the raw material for everything. As we travel, our ship might occasionally pass through a region that feels a bit denser, a bit cooler. These are the molecular clouds. These are the nurseries of the galaxy. They are vast, dark, and cold, often dozens of light years across. They are so dense with gas and dust that they block the light from the stars behind them, appearing as black splotches against the starry background. Inside these cosmic wombs, gravity works its magic, pulling pockets of gas together until they collapse under their own weight, heating up until nuclear fusion ignites in their cores, and a new star is born. As we fly by, we might see the glorious glow of one of these newborn stars, a hot, brilliant blue-white infant. Its intense radiation is now beginning to blow away the cocoon of gas and dust that formed it, like a butterfly emerging from its chrysalis. These regions, called emission nebulae, are some of the most beautiful objects in the galaxy, glowing with vibrant reds and pinks from energized hydrogen gas. The stars themselves here in the Orion Arm are a diverse lot. It's a real melting pot. We see the brilliant, hot, blue-white O and B-type stars. They are the rock stars of the galaxy, incredibly luminous, burning their hydrogen fuel at a prodigious rate. They live fast and die young, lasting only a few million years before going out in a spectacular supernova explosion, seeding the surrounding space with the heavy elements they forged in their cores. Then there are the steady, reliable stars like our own Sun, a G-type yellow dwarf. We are the middle class, the stable workers, burning our fuel steadily for billions of years, providing a steady haven for any planets that might be orbiting us. And finally, the most common stars in the galaxy, the red dwarfs. These are the M-type stars, small, cool, and incredibly frugal. They are so efficient with their fuel that they can shine for trillions of years, far longer than the current age of the universe. Most of the galaxy's stars are these dim, red, long-lived objects. As we continue inward, we cross a boundary of sorts, leaving the familiar streets of the Orion Arm and entering the next spiral arm inward, perhaps the Perseus Arm. The scenery changes noticeably. The spiral arms are not solid structures. You don't cross a fence into them. They are like waves of density, like traffic jams on a cosmic freeway. As stars, gas, and dust orbit the galaxy, they move in and out of these arms. But within the arms, the density is higher. The traffic is bunched up. So, as we enter the Perseus Arm, the number of stars in any given direction increases. The spaces between them on average begin to shrink. Remember, it's still mostly empty space. That average gap of several light years between stars is still the rule, but the average is getting smaller. The glow of the ISM is brighter here. The molecular clouds are larger and more frequent, and the brilliant blue-white newborns are more common. It's a more vibrant, more active part of the galactic city. This part of our journey takes tens of thousands of years. We are witnessing the galaxy in ultra-slow motion, seeing the grand structure unfold at a pace that is literally geological. And then we begin to approach the central region. The very character of the galaxy undergoes a dramatic shift. The thin, orderly disk begins to warp and swell. We are entering the bulge. The galactic bulge is the metropolis at the center of our continental scale city. It's a vast football-shaped or rugby ball-shaped swarm of stars. The orderly flatness of the disk is gone, replaced by a thick, teeming throng of stars in all directions. Above us, below us, all around us. The density here is exponentially higher. Let's put some numbers on it, simple ones. Out where we live in the galactic suburbs, there is about 0.004 stars in every cubic light year. That means you could fit a cube 1 light year on each side around our sun, and you'd find, on average, a tiny fraction of one other star. It's empty. In the bulge, that number skyrockets. In some parts of the inner bulge, there could be over 100, maybe even 1,000 stars in that same cubic light year volume. Imagine the night sky from a hypothetical planet orbiting a star deep within the bulge. It would be unlike anything we can comprehend. It wouldn't be a dark sky with pinpricks of light. It would be a blazing, perpetual twilight. Thousands of stars would be brighter than the planet Venus appears in our sky. The entire sky would be lit up with millions of stars visible to the naked eye. There would be no true darkness, ever. The combined light of so many stars would be enough to read by at midnight. It would be a sight both terrifyingly beautiful and utterly alien. The constellations would be meaningless. the sky would just be a solid, shimmering sheet of starlight. And at the very heart of this brilliant, dense, chaotic metropolis lies the anchor, the reason for all this crowding, the supermassive black hole, Sagittarius A star. We cannot see it. No light can escape it, but we can see its terrifying influence. We can observe stars orbiting frantically around nothing. They whip around this invisible point at speeds of thousands of kilometers per second, their orbits telling us the mass of the object they are circling. That mass is about 4.1 million times the mass of our Sun. Now, it's crucial to correct a common misconception. Sagittarius A star is not a cosmic vacuum cleaner, actively sucking everything in. From our distance, it's a gravitational anchor. Its influence is vast, but its physical size is tiny. Its event horizon, the point of no return, is only about 24 million kilometers across. That's smaller than the orbit of Mercury around our Sun. On our USA scale model, it would be smaller than a single atom at the very center of the continent. It's a pinprick of ultimate density, a silent, dark king sitting on the throne, its immense gravity governing the frantic dance of the stars around it, helping to shape the entire bulge that surrounds it. We fly past this monstrous, invisible presence and continue on our way, out through the bustling, star-choked bulge, back into the thinning disk. We pass through the spiral arms on the far side of the galaxy, a mirror image of our own side, watching the stellar density gradually decrease, the brilliant blue star-forming regions becoming less frequent, until we once again break through into the sparse, dark, and ancient countryside of the outer halo, finally emerging from the opposite edge of the galactic disk. We have done it. We have crossed the Milky Way. And how long did this magical light-speed journey take? 100,000 years. 100,000 years. Let's make that number land. Modern humans, Homo sapiens, have only been around for about 200,000 to 300,000 years. Our light-speed journey across the galaxy took half that time. All of recorded human history, the building of the pyramids, the rise and fall of Rome, the scientific revolution, the creation of the internet, all of that fits into the last 5,000 or 6,000 years. Our journey took 20 times longer than all of that. We were traveling at the ultimate speed limit of the cosmos, and it still took us an epoch. That isn't just a number. That is the final, humbling, and utterly inescapable truth of the sheer, mind-boggling scale of our galactic home. It is a vastness that transcends human history, a stage so large that our entire story is but a fleeting whisper somewhere in its quiet suburbs. But the story of the Milky Way's size isn't just about its stars and its empty spaces. It's also a story in time. We've been talking about the Milky Way as it is now, a magnificent spinning pinwheel of stars. But to truly know something, you have to know its story. Where did it come from? What shaped it? And where is it going? The size of our galaxy isn't just a snapshot. It's a single frame in an epic movie that has been playing for almost the entire age of the universe. So let's rewind the cosmic clock all the way back to the beginning. The universe itself is about 13.8 billion years old. Our galaxy, the Milky Way, is a cosmic elder. It began to form not long after the Big Bang itself, around 13.6 billion years ago. Just let that number sit for a moment. 13,600,000 years. How can we even comprehend such a depth of time? If you condense the entire history of the universe into a single calendar year, with the Big Bang at the stroke of midnight on January 1st, our Milky Way galaxy would have begun forming just a few days later, in early January. The Earth, by comparison, wouldn't form until mid-September. The entire span of human history would be the last few seconds before midnight on December 31st. Our galaxy is ancient beyond our everyday comprehension, but it didn't spring into existence as this beautiful, organized spiral we see today. That came much, much later. The early universe was a very different place. It was a dark, swirling sea of primordial gas, mostly hydrogen and helium, and that mysterious, invisible dark matter. There were no stars, no galaxies, just a faint, fading afterglow from the Big Bang and these vast, slowly cooling clouds. Gravity is the great sculptor of the cosmos, and it went to work on these clouds. Tiny, random ripples in the density of this primeval soup began to amplify. Patches that were ever so slightly denser began to pull more matter towards them. These were the seeds, the proto-galactic clouds, that would one day become galaxies. So, picture the infant Milky Way not as one single thing, but as a chaotic, swirling mess of dozens, perhaps even hundreds, of these smaller gas clouds and clumps of dark matter, all slowly, inevitably, falling together and merging. It was a violent and chaotic process, a cosmic demolition derby that lasted for billions of years. There was no gentle coming together. It was a series of colossal collisions. With each merger, the growing baby galaxy would get a jolt. Its gas would be stirred up, triggering furious waves of new star formation. The sky in those early epochs would have been a terrifyingly spectacular sight, filled with the brilliant, short-lived flashes of massive first-generation stars going supernova, their explosions seeding the surrounding gas with the first heavy elements, the carbon, oxygen, and iron that would one day be essential for planets and life. And this process of growth through cannibalism never really stopped. Our Milky Way is not a peaceful, isolated island. It exists in a gravitational neighborhood, and it is the biggest, most massive kid on the block. It has a powerful gravitational pull, and it uses it to consume its smaller neighbors. It continues to do so even today, right now as we speak. We have the evidence. Astronomers, using powerful telescopes, can see the ghostly trails of stars stretching across our galactic halo. These are tidal streams, the cosmic scars of dwarf galaxies that ventured too close to our galaxy. The gravity of the Milky Way is like a powerful tidal force. It has stretched these unfortunate galaxies out, pulling them apart like cosmic taffy, until their stars are no longer a distinct cluster but a long, shimmering river of stars, wrapping around our galaxy in vast, elegant arcs. The most famous of these is the Gaia Sausage, or the Sausage Galaxy, the remains of a dwarf galaxy that collided with the Milky Way about 8 to 10 billion years ago and was utterly shredded, its stars now forming a significant part of our galactic halo. It's a stark reminder that the Milky Way is a dynamic, evolving beast, not a static picture in a textbook. It's a predator, still growing and changing. And this brings us to the future, to the next, and perhaps final great chapter in our galaxy's life story. It's not done growing. In about 4 to 5 billion years, the Milky Way is destined for the collision of a lifetime. Our nearest large galactic neighbor, the beautiful Andromeda Galaxy, is on a collision course with us. Now, when we say collision course, it sounds terrifying, like two cars smashing into each other on a highway. But we must remember the most important lesson we've learned about our galaxy. Its overwhelming, dominant feature is not the stars, but the empty space between them. Andromeda is hurtling towards us at a tremendous speed, about 110 kilometers per second. That's fast enough to travel from the Earth to the Moon in under an hour. But the distance between us is so immense, about 2.5 million light-years, that this cosmic rendezvous is still billions of years away. So what will happen when we meet? It will not be a catastrophic crash of stars. It will be a slow, majestic, gravitational dance. The spaces between stars are so phenomenally vast that when the two galaxies merge, it is incredibly, almost unthinkably unlikely that any two stars will actually physically collide. It would be like taking two handfuls of fine sand and tossing them into the wind so that they pass through each other. The chances of two individual grains of sand hitting each other are virtually zero. Instead, picture two vast swarms of bees, each containing hundreds of billions of bees, gently passing through one another. Each individual bee, each star, will follow its own path, largely unaware of the others, guided only by the combined gravitational field of the entire swarm. They won't crash, they will swing past one another in long, graceful arcs, but their overall shapes will be utterly distorted. The beautiful, delicate spiral arms of both the Milky Way and Andromeda will be stretched and torn apart by tidal forces. The two galaxies will become a tangled, messier, and much larger blob of stars. They will swing past each other, then fall back together, and then swing past again, in a series of ever-tightening loops over the course of 1 billion years. It will be a slow-motion merger, a cosmic ballet choreographed by gravity. Eventually, after this long, chaotic dance, the two galaxies will lose their separate identities and settle down, merging into a new, larger type of galaxy. The neat, flat spiral disks will be gone, replaced by a more featureless, football-shaped swarm of stars called an elliptical galaxy. Astronomers have already given this future galaxy a name, Milky Way. It's a fitting name for the combined legacy of our two great star cities. What will happen to us, to our solar system, during all this? Our sun will still be shining then, though it will be brighter and older. Our solar system will likely be flung out into a much different, much larger orbit within this new Milky Way galaxy. We probably won't be anywhere near the new galactic center. We'll be thrown out into the distant suburbs, but we will almost certainly survive the encounter physically. The real change will be in the sky. For any beings living on Earth at that far future time, perhaps our descendants, perhaps something else entirely, the night sky will be utterly transformed. It will be a dazzling, constantly changing display. As the merger progresses, the Andromeda Galaxy, which today is a faint, fuzzy smudge in our sky, will grow larger and larger, eventually filling the entire heavens. The familiar band of our Milky Way will be joined by a second brilliant river of light, and then the two will churn together into a spectacular, chaotic canvas of countless stars. It will be the greatest light show in the history of our planet, a billion-year-long fireworks display marking the end of our galaxy as we know it and the birth of something new and grand. It's a story that stretches from the very dawn of time to a future so distant it challenges imagination, and it's the story of the home we are just beginning to understand. So when we ask, how big actually is our Milky Way galaxy? We have to think in multiple dimensions. It is big in population, 1 to 400 billion stars. It is big in space, 100,000 light years across, a continent of emptiness with grains of sand for stars. It is big in time, a 13.6 billion year history of formation, growth, and future collision. And it is big in mass, containing not just the visible stars and gas, but dominated by the mysterious, invisible hand of dark matter, whose gravitational pull is the true architect of the galaxy's grand design. We are a part of this. The calcium in your bones, the iron in your blood, the oxygen you breathe, these elements were forged in the hearts of long-dead stars that lived and died in this galaxy before our sun was even born. We are not just living on a planet. We are living in a galaxy. We are the Milky Way, become conscious of itself. We are a tiny, fleeting part of this immense, rotating, evolving cosmic structure. So the next time you find yourself under a clear, dark sky, look up. Find that faint, milky river of light, and remember what you are truly looking at. You are not looking at a distant external thing. You are looking at your home. You are looking edge-on into the disk of a continent-sized city of stars from your vantage point in the quiet suburbs. You are seeing the combined light of billions of distant suns, the central bulge glowing like a distant city center, the dark lanes of cosmic dust clouds blocking the light from beyond. You are seeing the scale of your own existence. It is a humbling, awe-inspiring, and profoundly beautiful sight. And now you know just how big it actually is. And so, there you have it. Our little marble, orbiting its grain of sand sun in a quiet suburb of a continent-sized city of stars. A city that is itself growing, changing, and dancing with its neighbors in the infinite black. It's a perspective that is at once both humbling and incredibly uplifting. We are so small, and yet we are a part of this. We get to be the part that can look up and understand and feel awe. I hope this journey across the cosmos has brought a little wonder and peace to your evening. Wherever you are, whatever time it is, I hope you carry this feeling of cosmic connection with you as you drift off. If this peaceful exploration helped you unwind or see the universe in a new way, please consider supporting our community here on Happy Sleep. Subscribing to the channel helps you never miss our next journey into relaxation and wonder. And if you felt inspired, leaving a like is a wonderful way to let me know. Most of all, I'd love to hear from you. As you float here in our little corner of the Milky Way, tell me in the comments, where in the world are you listening from tonight? What's one thought or feeling you're taking with you from our journey? From all of us here at Hafi Sleep, thank you for sharing this time and space. Sleep well, dream deeply, and may your dreams be as vast and peaceful as the galaxy itself. Good night.